The water looks harmless at first. Sunlight breaks into clean bands as it passes through the upper layers, scattering across a shallow reef where sand ripples lie undisturbed and coral heads sit like old stone ruins. A pufferfish moves through this space without urgency, hovering rather than swimming, adjusting position with tiny flicks of its fins. There is no chase, no threat display, no sign of violence. Its round body drifts forward with the confidence of something that does not expect to be challenged. Around it, smaller fish keep their distance without obvious fear, as if obeying a rule they learned long ago but no longer question. This calm is not accidental. It is enforced by chemistry. The puffer's movement is inefficient by predator standards. It does not slice through water like a barracuda or glide with the silent certainty of a shark. Instead, it pulses gently, relying on fine motor control rather than speed. This would seem like a disadvantage in a reef crowded with hunters, yet the puffer behaves as if speed is irrelevant. When a shadow passes overhead and a larger fish drifts closer, the puffer does not flee. Its response is delayed, almost dismissive, until the distance closes to a point that would trigger panic in nearly any other species. Only then does the transformation begin. Water is pulled rapidly into the puffer's stomach, not as a reflexive gulp, but as a coordinated expansion driven by specialized muscles and elastic tissues. The body swells outward, doubling, sometimes tripling in volume. Spines that once lay flat against the skin rise into rigid defensive spikes, turning a soft-bodied fish into an awkward spherical obstacle. The predator halts its approach, confused less by the change in size than by what that change represents. The puffer is no longer prey. It has become a warning. Inflation alone is not the true defense. Many animals can appear larger when threatened, but appearance only works if the bluff is credible. In the puffer's case, the danger is real and far more severe than sharp spines or a mouthful of indigestible flesh. Embedded within the tissues of this fish is one of the most potent natural toxins found in the ocean, a substance that does not attack by destroying cells or burning tissue, but by quietly shutting down communication inside the body. Tetrodotoxin does not cause pain in the way venom often does. It causes silence. At the level of nerves and muscles, movement depends on electrical signals traveling along nerve fibers and crossing tiny gaps to trigger muscle contraction. Tetrodotoxin interferes with this process by blocking sodium channels in nerve cell membranes, the microscopic gateways that allow electrical impulses to propagate. When these channels are blocked, the signal stops. Muscles receive no instruction to contract. Limbs, fins, gills, and eventually the diaphragm simply fail to respond. The mind may remain fully aware, but the body no longer listens. For a predator that bites a puffer without understanding this risk, the consequences are immediate and catastrophic. The first effect is often loss of coordination. Fins stop responding with precision. Swimming becomes erratic, then sluggish. As the toxin spreads, muscles weaken further, and the predator may sink or roll, unable to maintain balance in the water column. In severe cases, respiratory muscles cease functioning, and the animal suffocates without external injury. There is no dramatic struggle, no visible wound. The hunter simply stops working. This is why puffers are rarely attacked more than once by the same predator. In reef ecosystems, learning is expensive, but it is also fast. A predator that survives an encounter with a mildly toxic puffer may experience hours or days of impaired movement, confusion, and vulnerability. That memory is reinforced every time it encounters the distinctive shape, swimming style, or coloration associated with puffers. Over time, avoidance becomes instinctive. The puffer does not need to flee. The ecosystem moves around it. The toxin itself is not produced entirely by the fish in isolation. In many puffer species, tetrodotoxin originates from bacteria present in their diet, accumulated through the food web and stored in the liver, skin, and other tissues. This means toxicity varies widely depending on species, habitat, and available prey. Some puffers are only mildly toxic, while others carry doses strong enough to kill multiple large animals. The fish is not born dangerous by default. It becomes dangerous by eating the right things in the right environment. This dietary link has profound ecological implications. Changes in reef composition, prey availability, or microbial communities can alter toxin levels over time. A puffer in one region may be relatively harmless, while a closely related species elsewhere is lethally potent. Predators do not distinguish these nuances at first, which reinforces the rule of avoidance even when the risk is inconsistent. In this way, poison creates a protective umbrella, not only for the puffer itself, but for other species that resemble it closely enough to benefit from mistaken identity. The puffer's slow breathing during inflation reveals another layer of adaptation. As its body expands, gill movement becomes more deliberate, conserving energy and oxygen while maintaining control. Panic would be dangerous here, as rapid respiration could increase toxin circulation within its own body or compromise buoyancy. Instead, the puffer remains composed, holding its inflated form only as long as necessary before gradually releasing the water and returning to its original shape. This restraint suggests a finely tuned balance between defense and self-preservation. For fish that share the reef, the presence of puffers reshapes behavior patterns. Predators alter hunting routes, avoid certain feeding grounds, or switch prey preferences entirely. Smaller fish may cluster near puffers, exploiting the reduced predation pressure in their immediate vicinity. In this way, poison does not simply protect the animal that carries it. It reorganizes relationships across the ecosystem. Who hunts where, who risks what, and who survives long enough to reproduce are all influenced by the silent threat puffers represent. Humans, however, do not always respect these rules. In certain cultures, puffer fish are prepared as a delicacy, a practice that demands extreme precision and expertise. The margin for error is effectively non-existent. A single mistake in handling, a trace of contaminated tissue left behind, can deliver enough tetrodotoxin to paralyze respiratory muscles within minutes. There is no antidote. Survival depends entirely on supportive care, and the body's ability to clear the toxin before oxygen deprivation causes irreversible damage. This is not a poison that forgives curiosity or bravado. The danger lies not in aggression, but in assumption. The puffer does not attack. It does not chase. It does not inject venom. Its weapon is entirely passive, activated only when someone else decides to bite, touch, or consume it. This makes it one of the most effective deterrents in the ocean because it shifts responsibility onto the predator. The message is simple and absolute. Do not eat this. From an evolutionary perspective, this strategy is remarkably efficient. Rather than investing energy in speed, strength, or complex weapons, the puffer relies on a chemical shortcut that neutralizes threats regardless of size or skill. A massive predator gains no advantage over a smaller one if both are equally susceptible to nerve blockade. In this sense, tetrodotoxin levels the playing field, allowing a slow, awkward fish to coexist alongside some of the most capable hunters in the sea. Over time, this has allowed puffers to occupy niches that would otherwise be inaccessible. They feed openly, cruise exposed areas, and invest energy in reproduction rather than constant vigilance. Their eggs and juveniles still face high mortality, but adulthood brings a level of security rare among reef fish. This security, however, is conditional. Remove the toxin from the equation, and the puffer becomes what it appears to be: slow, conspicuous, and easy to catch. This dependence on chemistry highlights a broader truth about marine ecosystems. Power is not always visible. The most dangerous animals are not necessarily those with teeth or speed, but those that manipulate the rules of physiology itself. By interrupting nerve signals, the puffer bypasses armor, muscle, and instinct. It attacks the underlying code that makes movement possible. In doing so, it enforces a boundary that most species quickly learn not to cross. As the puffer deflates and resumes its gentle cruising, the reef settles back into motion. Predators drift away. Smaller fish return to feeding. The moment of tension passes without drama, leaving no trace except memory. The puffer has not chased anything off. It has not struck or wounded an enemy. It has simply existed, carrying within its body the potential to turn movement into stillness. In the ocean, that is often enough. At first, there is nothing to see. The seabed looks ordinary, almost boring, a patchwork of pale sand, broken coral fragments, and dark stones scattered as if dropped carelessly by the tide. Light ripples across the bottom in slow, shifting bands, blurring edges and flattening contrast. Small reef fish pass through without hesitation, focused on grazing and patrol rather than inspection. Nothing here announces danger. Nothing moves. That is precisely the point. The stonefish is already present, fully exposed and perfectly hidden. Its body presses into the sand with the weight and stillness of something that belongs there, its outline broken into irregular bumps and ridges that mimic rubble and rock. The skin is mottled with blotches of brown, grey and muted green, textures that scatter light instead of reflecting it. Algae cling to its surface, not as decoration but as camouflage enhanced by time. Even close, even when the camera lingers, the stonefish resists recognition. It does not resemble a fish so much as a mistake in the landscape, an uneven patch the eye slides past without question. This is not the camouflage of a hunter preparing to strike. The stonefish does not stalk or pursue. It waits. It does not rely on speed, intelligence, or strength. Its survival strategy is simpler and more ruthless. It turns the act of contact itself into a weapon. Only when the angle shifts and the light changes do the dorsal spines become visible. They rise from the back like a row of short, thick needles, each tipped with a sharp point and connected to venom glands beneath the skin. From above, these spines blend into the surrounding debris, mistaken for broken coral or shell fragments. From the side, they look less like fins and more like mechanical components, rigid and purposeful. They are not raised in warning. They are always ready. The stonefish does not threaten. It does not display. It does not flee. Instead, it transforms the seabed into a trap that activates only when something makes a mistake. When pressure is applied to the spines, whether by a predator's mouth, a passing fish's flank, or an unwary foot, the mechanism engages instantly. The spine penetrates flesh, and venom is injected directly into the wound, delivered not by aggression but by compression. This is contact-activated weaponry, as automatic and unforgiving as a spring-loaded syringe. The venom itself is a complex cocktail of proteins designed to cause intense pain, tissue disruption, and systemic effects. Unlike toxins that rely on ingestion or absorption over time, stonefish venom acts immediately. It interferes with nerve signaling, damages cells, and triggers a cascade of physiological responses that overwhelm the victim's ability to function normally. For fish, this often means sudden loss of coordination, intense distress, and retreat. For larger animals, the pain alone is enough to enforce instant avoidance. The stonefish does not need to chase predators away. It trains them. This training reshapes the reef. Fish that survive an encounter with a stonefish remember the shape, the texture, the wrongness of that contact. They learn not to mouth unfamiliar lumps on the seabed. They learn to give wide clearance to certain silhouettes, even when hunger presses. Over time, this learning spreads indirectly through the ecosystem. Predators that avoid stonefish habitats leave pockets of relative safety for smaller species. Grazers alter their routes. Hunting patterns bend around invisible hazards. The stonefish, motionless and silent, influences behavior far beyond its immediate reach. What makes this strategy especially dangerous is that it requires no decision on the stonefish's part. There is no timing to get wrong, no energy expenditure to manage. The fish can remain still for hours or days, its metabolism slowed, conserving resources while its defenses remain fully active. Even death does not immediately neutralize the threat. The spines remain venomous for some time, turning a lifeless body into a lingering hazard. In this way, the stonefish weaponizes not only movement, but assumption. Anything that treats the seabed as passive terrain is at risk. For reef fish, the danger often comes during feeding. A curious bite, a careless brush, or an attempt to swallow what appears to be a harmless rock can trigger envenomation. The effect is swift. Pain signals overwhelm the nervous system, muscles spasm or fail, and the fish retreats in confusion or collapses outright. Survival depends on dosage, location, and the animal's size, but even non-fatal encounters are costly. Injured fish become vulnerable to secondary predation, infection, or starvation. One mistake can ripple outward, altering population dynamics in subtle but lasting ways. Humans enter this equation not as predators, but as careless participants. The stonefish is most dangerous to people precisely because it lives in shallow water, the same zones favored for wading, snorkeling, and reef walking. Bare feet press into sand. Hands reach for balance. Attention drifts upward toward the surface rather than downward toward the substrate. In these moments, the stonefish does not need to move or react. The human does all the work. When a foot comes down on a stonefish, the spines penetrate deeply, injecting venom directly into soft tissue. The pain is immediate and overwhelming, often described as unbearable, not because of exaggeration, but because of the venom's direct action on nerve endings and surrounding cells. The body responds with swelling, muscle weakness, nausea, and in severe cases, systemic effects that can escalate rapidly. Medical treatment is required not because the stonefish chased or attacked, but because the victim unknowingly activated a trap. This inversion of responsibility is what makes the stonefish so effective and so feared. It does not hunt you. You injure yourself by failing to recognize it. In evolutionary terms, this is an extraordinary adaptation. Rather than evolving better senses or faster reactions, the stonefish evolved a form that punishes interaction itself. The safest response is total avoidance, and the fish's camouflage ensures that avoidance requires constant vigilance. The production of venom is tightly integrated into the stonefish's anatomy. Glands at the base of each dorsal spine synthesize and store the venom, ready to be delivered under pressure. This venom is energetically expensive to produce, but the cost is offset by the dramatic reduction in predation risk. Unlike animals that rely on repeated attacks or displays, the stonefish can afford to be lazy. Its defense works even when it is half buried, asleep, or injured. It is a system designed to function under worst-case conditions. This design reveals something important about reef ecosystems. Danger does not always announce itself. Some of the most effective survival strategies rely on invisibility and inevitability rather than speed or strength. The stonefish thrives not by outcompeting others in a chase, but by turning the environment itself into an extension of its body. Sand becomes armor. Stillness becomes threat. Even its hunting strategy reflects this philosophy. Stonefish are ambush predators, feeding on small fish that stray too close. They do not pursue. They wait until prey drifts within range, then strike with a sudden gulp that creates suction, pulling the victim into the mouth before it can react. This feeding behavior pairs perfectly with their defensive strategy. The same stillness that hides them from predators also hides them from prey. The reef, in effect, moves around the stonefish without noticing it until it is too late. There is a quiet irony here. The stonefish is one of the most venomous fish in the ocean, yet it rarely needs to use its venom offensively. Its reputation does the work for it. Predators learn. Humans warn each other. Entire safety protocols are built around avoiding contact with something that does not chase, roar, or strike from a distance. Fear arises not from action, but from potential. In ecological terms, this creates zones of behavioral tension. Areas where stonefish are common become places of caution. Movement slows. Foraging becomes more deliberate. This can reduce grazing pressure on certain algae or invertebrates, indirectly shaping reef composition. The presence of a stationary venomous animal alters flow patterns of life in ways that are difficult to measure but impossible to ignore. The stonefish remains where it began, unmoving as fish resume their routines nearby. A fin brushes past, just close enough to hint at danger, then veers away. Nothing dramatic happens. No strike, no explosion of motion. The weapon is not used. That is success. In the logic of the stonefish, survival is achieved not by confrontation, but by ensuring that confrontation is always a losing choice for the other side. This is what makes the stonefish top tier among dangerous marine animals. It does not rely on aggression. It does not need to detect you first. It does not even need to be alive in the moment of contact. Its defense is embedded in its shape, its position, and its patience. You do not get attacked by a stonefish. You make a single wrong assumption, and the ecosystem corrects you instantly. As the tide shifts and light fades, the seabed looks unchanged. The same sand, the same stones, the same silence. But one of those shapes is not terrain. It is a reminder that in the ocean, the most dangerous animals are often the ones that do nothing at all. The reef is crowded, busy with motion that never quite settles. Schools of small fish weave through coral heads like sparks blown sideways by a current, while larger bodies patrol the edges, testing the space for weakness. Predation here usually depends on speed, surprise, or numbers. Most hunters stay close to cover, darting in short bursts before retreating back into safety. Then a lionfish enters the frame, and the rules loosen. It moves slowly, almost lazily, hovering above the reef with deliberate control. Long pectoral fins unfurl outward in a wide arc, translucent membranes stretched between spines that radiate like the ribs of a fan. Stripes of red, white, and brown break up the outline of its body, bold and conspicuous rather than cryptic. In a place where most prey survives by blending in or fleeing fast, the lionfish does neither. It announces itself openly, drifting through exposed water as if daring the reef to react. The reaction is hesitation. Small fish sense the disturbance immediately, but instead of scattering into open water, they compress inward towards structure. The lionfish adjusts its position with subtle fin movements, rotating slowly as its fins spread wider, forming a loose circular barrier. The effect is not explosive or frantic. It is controlled pressure. The prey find themselves pressed closer to coral, their escape routes narrowing as the fin rays block lateral movement. This is fin fencing, a hunting strategy that relies on geometry rather than speed. The lionfish's fins do not strike. They do not lash or grab. They simply exist in the right place at the right time, shaping the behavior of other animals through presence alone. Each spine is rigid and sharp, but the true deterrent lies beneath the surface. At the base of these spines are venom glands, and running along each spine are grooves that act as channels. When a spine penetrates flesh, venom travels down these grooves and into the wound, delivered passively but efficiently. These are not offensive weapons meant to kill prey. They are needles on a shield. This distinction matters. The lionfish does not inject venom into the fish it eats. Prey are captured whole, drawn into the mouth by a sudden expansion of the buccal cavity that creates suction strong enough to overcome frantic tail beats. The venom exists for a different audience entirely. It is a message to predators watching from the edges, considering whether this slow-moving, flamboyant fish might be an easy meal. The answer is no. Predators that have learned the cost of contact with lionfish recognize the display instantly. The spread fins are not just visual exaggeration. They are a warning structure, signaling that any attempt to bite or ram will result in pain, swelling, and impaired function. For reef predators that rely on precision and repeated hunting success, even temporary injury is unacceptable. A damaged mouth or face can mean starvation. As a result, lionfish enjoy a level of freedom rare among reef hunters. They can glide slowly, hunt methodically, and operate in open spaces without constant threat. This freedom shapes their behavior. While many predatory fish hunt in bursts, lionfish can afford patience. They approach prey gradually, herding them with fin movements rather than chasing them down. The prey, confused by the encroaching fins and reluctant to dash past the spines, often freeze or cluster tightly. In these moments, the lionfish closes the distance just enough. Its mouth opens, water rushes inward, and the prey disappears without a struggle. There is no bite, no tearing. The hunt ends as quietly as it began. The venom that makes this confidence possible is metabolically costly to produce, but its payoff is immense. By reducing predation risk, the lionfish reallocates energy away from vigilance and escape into growth, reproduction, and sustained hunting effort. This has consequences not just for individual fish, but for entire reef systems. Lionfish can feed more frequently and on a wider range of prey sizes than many native predators, especially in environments where they face little competition or control. The physiology behind this system is elegant. Venom glands at the base of the dorsal, anal, and pelvic spines synthesize a protein-based venom that causes intense pain, inflammation, and sometimes systemic symptoms when delivered. The venom does not need to be actively injected. Pressure alone is sufficient. When a predator's tissue compresses the spine, venom flows along the grooves and into the puncture wound. This means the lionfish does not need to time a strike or aim a sting. Any contact is enough. For reef fish that accidentally brush against a lionfish during a chase or territorial dispute, the consequences are immediate. Sudden pain triggers retreat, disorientation, or erratic movement. Even non-lethal encounters are remembered. Over time, the reef develops an avoidance pattern. Lionfish are given space. This social distance further amplifies their hunting success, as prey species have fewer cues to associate lionfish presence with immediate danger compared to faster, more aggressive predators. Humans encounter this system from a different angle. Divers, snorkelers, and handlers are most often stung not because lionfish attack, but because the fish is underestimated. Its slow movement and ornate appearance invite curiosity rather than caution. A hand reaches too close. A fin brushes past a leg. A spear misses its mark during removal efforts. The spines do the rest. Pain radiates outward from the puncture site, swelling follows, and in some cases nausea, dizziness, or weakness set in. These symptoms are rarely life-threatening with proper care, but they are severe enough to command respect. This mismatch between appearance and consequence is part of the lionfish's evolutionary success. Bright coloration, often associated with warning signals in nature, does not deter all threats. Some predators test anyway. The venom ensures that testing is punished swiftly. Once learned, the lesson persists. The reef remembers. From an ecological perspective, this strategy becomes especially powerful in regions where lionfish are not native. Without evolved predators capable of tolerating or circumventing the venom fence, lionfish populations can expand rapidly. Their bold hunting style allows them to reduce local prey populations significantly, including juvenile fish critical to reef resilience. This is not because lionfish are uniquely efficient killers, but because their venom-enabled confidence removes constraints that normally limit predatory impact. In their native range, this balance is moderated by long-term evolutionary relationships. Predators recognize lionfish early. Some learn to attack from behind or target non-spined areas, though such strategies are risky and rare. In unfamiliar ecosystems, that knowledge does not exist. The venom fence becomes absolute, and the lionfish hunts as if unopposed. Watching a lionfish glide through open water, it becomes clear that venom here is not about aggression. It is about permission. The ability to hunt slowly, visibly, and repeatedly without fear transforms the lionfish into a persistent pressure on the reef. It does not need to sprint or ambush from darkness. It can operate in daylight, in full view, reshaping prey behavior through sustained presence. There is a subtle irony in this. The lionfish's venom is not particularly useful for offense, yet it enables one of the most effective hunting styles on the reef. By outsourcing danger to a passive defense, the fish frees itself from the constraints that shape most predator behavior. It becomes bold, not because it is fast or strong, but because nothing wants to make contact with it. As the lionfish completes its slow circuit and folds its fins back into a narrower profile, the reef resumes its normal rhythm. Small fish disperse cautiously. Predators return to their patrols at a respectful distance. The lionfish does not chase or threaten. It simply remains, a floating boundary of needles and consequence. In a world governed by movement and reaction, its greatest weapon is the confidence to move openly, knowing that the cost of touching it is too high for almost anyone to pay. The reef narrows into corridors where light fades and movement slows. Coral heads rise close together here, creating a maze of cracks and overhangs where open water hunters lose their advantage. Fish that live in these spaces rely on agility and instant acceleration. slipping through gaps too small or irregular for larger predators to follow. This is terrain designed to frustrate pursuit. It is also the terrain where sea snakes move with absolute control. A sea snake threads through the coral with a smooth, deliberate motion, its body bending in slow waves that never seem hurried. Unlike eels or moray predators that wedge themselves into crevices with brute force, the snake flows through these spaces as if poured into them. Its laterally flattened body acts like a ribbon, slicing sideways through water with minimal resistance. Each movement is efficient, conserving energy in an environment where sudden bursts are costly and often unnecessary. The snake does not search widely. It knows exactly where to look. Vision guides much of this movement. Sea snakes rely heavily on sight to locate prey hiding among coral branches or pressed against rock. Their eyes, positioned high on the head, scan ahead as the body advances, reading the subtle shifts in posture and color that betray living fish. The reef appears crowded and chaotic, but to the snake, it is segmented into zones of probability, pockets where prey is likely to hesitate or pause. This is where the snake slows further, its head angling slightly as it tests distance and timing. The strike is not dramatic. There is no coiling, no lunging display. The snake simply closes the gap with a short, precise extension of the head, delivering a bite that lasts barely long enough to register. Small, fixed fangs pierce the prey's flesh, and venom is injected almost instantly. The snake does not hold on. It does not wrestle or constrict. As soon as the venom is delivered, the snake releases and withdraws, already turning away as the prey reacts. At first, the fish attempts to flee. Its body kicks hard, tail beating in uneven bursts as it darts forward. But within seconds, something is wrong. Movements lose symmetry. Turns become wider and less controlled. The fish struggles to maintain orientation, drifting off balance as muscle coordination begins to fail. The venom has taken effect, not by damaging tissue or causing pain, but by interfering with the signals that allow muscles to function together. Sea snake venom is a chemical shortcut through the problem of escape. In tight reef spaces, prey do not need to be overpowered. They only need to lose control. The venom targets neuromuscular junctions, blocking the transmission of signals between nerves and muscles. Without these signals, muscle fibers cannot contract effectively. Swimming becomes labored, then impossible. The fish is still alive, still aware, but its body no longer responds with precision. This rapid immobilization is the core of the sea snake's hunting strategy. Rather than risking injury by holding on to struggling prey in confined spaces, the snake lets chemistry do the work. The prey weakens on its own, drifting or sinking slightly as fin movements slow. Only then does the snake return, tracking the fading motion with calm certainty. The second approach is unhurried. There is no resistance now, no frantic escape attempt. The snake aligns its jaws, opens wide, and begins to swallow the fish head first, muscles working in steady waves to draw the prey down. The venom that makes this possible is produced in specialized glands located in the head, connected directly to the fangs by ducts. These glands synthesize complex mixtures of proteins designed specifically for rapid immobilization. Unlike venoms that cause widespread tissue damage or inflammation, sea snake venom is highly focused. Its efficiency reduces the amount needed per strike, allowing the snake to conserve venom while maintaining lethality. This is crucial in an environment where prey encounters may be frequent, and refilling venom stores takes time and energy. For reef fish, the threat posed by sea snakes is subtle but severe. There is often no warning. The bite is fast and minimally disruptive, and by the time the prey registers danger, escape is already compromised. This favors prey species that maintain constant vigilance and rapid response, but even these adaptations have limits in narrow spaces. Over evolutionary time, fish that share habitat with sea snakes develop behaviors that reduce risk, such as avoiding certain crevices or reacting instantly to serpentine shapes. Still, the balance remains tilted in favor of the snake. The sea snake's approach also reduces its own exposure to injury. Holding on to prey with teeth or jaws risks damage, especially when prey have spines, sharp fins, or the ability to thrash violently. By biting and releasing, the snake avoids prolonged contact. This is especially important in reef environments where a moment of distraction can attract secondary predators. The venom acts as a delayed restraint, allowing the snake to withdraw and assess the situation before committing to consumption. Humans encounter this system rarely, but when they do, the stakes are high. Sea snakes are generally non-aggressive and often indifferent to divers, but accidental contact or provocation can result in envenomation. The danger lies not in dramatic immediate pain, but in the venom's potency and delayed effects. Sea snake venom is among the most toxic of all snake venoms by weight, and even small amounts can cause serious neuromuscular symptoms. Initial signs may be subtle, including muscle stiffness or weakness, but these can progress over hours as venom spreads. Paralysis of respiratory muscles is the most serious risk, and without prompt medical intervention, outcomes can be severe. This delayed onset is what makes sea snake bites particularly dangerous. The absence of immediate pain can lead to underestimation of the injury, delaying treatment until symptoms escalate. Caution, awareness, and respect for space are the most effective defenses. From an ecological perspective, the sea snake's venom-driven hunting strategy allows it to occupy niches that other predators cannot exploit effectively. In dense coral systems, where ambush space is limited and prey can vanish into cracks instantly, venom compensates for lack of speed. The snake does not need to outrun its prey. It only needs to touch it once. This shifts the balance of power in environments where physical pursuit would otherwise fail. This strategy also influences prey distribution. Fish may avoid certain reef structures known to harbor sea snakes, altering grazing patterns and local species composition. Over time, these micro-adjustments ripple outward, subtly shaping reef ecology. The presence of venomous predators affects not just who gets eaten, but where and how other animals choose to live. The sea snake itself is finely tuned to this lifestyle. Many species possess cutaneous respiration, allowing them to absorb oxygen through their skin, reducing the frequency of surfacing for air. This adaptation supports long hunting periods in complex reef environments, where surfacing repeatedly would break stealth and waste energy. Combined with efficient swimming and venom-based immobilization, this makes sea snakes remarkably effective predators in three-dimensional spaces. As the snake finishes swallowing its prey, it pauses briefly, body settling against the coral as it reorients. The reef continues around it, unaware of the exchange that just occurred. Small fish resume their movements. Crustaceans pick along the rock. The snake glides onward, searching for the next pocket of vulnerability. What makes sea snakes so effective is not aggression or speed, but restraint. They do not chase. They do not overpower. They remove the very ability to flee. In the narrow corridors of the reef, where escape routes are short and mistakes are costly, venom turns movement itself into a liability for prey. The snake does not need to be faster than its target. It only needs to ensure that the target cannot swim. In this way, sea snakes embody one of the ocean's most efficient survival strategies. They solve the problem of hunting in confined spaces not by changing the environment, but by changing the rules of physiology. Muscles that cannot move are muscles that cannot escape. The reef remains complex and crowded, but for the sea snake, complexity is an advantage. Every crack is a funnel. Every hesitation is an opening. And every successful bite turns motion into stillness, long before the prey ever realizes the chase is over. The current moves gently across the reef, lifting and lowering clusters of tentacles that look more like soft plants than animals. They sway in unison, translucent fingers reaching into open water, bending with each passing surge as if feeling their way through the space. From a distance, the sea anemone blends into the scenery, another decorative flourish attached to rock or coral, adding texture to an already crowded landscape. Nothing about it suggests urgency or threat. It does not swim. It does not chase. It does not even close its tentacles unless something touches them. And yet, within this apparent stillness, is one of the fastest and most ruthless weapons in the ocean. Up close, the illusion breaks down. Each tentacle is not a simple limb, but a living field of microscopic machinery. The surface is densely packed with specialized cells called nematocysts. each one a coiled, pressurized capsule containing a tiny harpoon tipped with toxin. These structures are not triggered by thought or intent. They fire automatically, faster than any nerve signal could travel, the instant they detect the right combination of physical contact and chemical cues. There is no warning and no hesitation. Touch equals discharge. A small fish drifts too close, brushing a tentacle as it turns. The reaction is instantaneous. At the microscopic level, thousands of nematocysts explode outward, each firing its harpoon into exposed skin or delicate gill tissue. The force is generated not by muscle, but by osmotic pressure stored within the cell, released in a fraction of a second. This is one of the fastest cellular actions known in biology. By the time the fish registers contact, the damage is already done. The toxins delivered are not meant to kill outright in every case. Instead, they disrupt basic physiological processes. Ion channels in cell membranes are affected, nerve signaling is altered, and muscle coordination falters. For small prey, this can mean immediate immobilization. Fins spasm or lock. Breathing becomes erratic as gill tissue reacts to the sting. Even when prey is not instantly paralyzed, the stress response is severe enough to slow escape, making capture inevitable. The anemone's tentacles curl inward, guiding the compromised animal toward the central mouth, where digestion begins externally before ingestion. What makes this system especially effective is its distribution. The anemone does not rely on a single sting or point of contact. Its entire surface is armed. Every tentacle is a minefield, every centimeter covered in autonomous weapons that require no coordination. This allows the anemone to remain passive, expending minimal energy while maintaining constant readiness. In an environment where energy efficiency determines survival, this is an extraordinary advantage. These nematocysts are not external additions. They are built into the anemone's tissue as it grows, manufactured continuously as part of normal cellular turnover. Old cells are replaced. New harpoons are assembled. The weapon system renews itself automatically. Damage or loss of tentacles does not permanently disarm the anemone, because regeneration restores both structure and armament. This makes the anemone resilient in a way that many mobile predators are not. For fish navigating the reef, this creates invisible boundaries. Areas around anemones become zones of caution. Species that have learned to recognize the distinctive shapes and movements of anemone tentacles alter their routes accordingly. Grazers detour. Juveniles keep their distance. Predators avoid chasing prey too close to these living traps, knowing that a misjudged turn could result in injury or disorientation. Over time, these avoidance behaviors shape traffic patterns across the reef, influencing who feeds where and how often. Yet, not all fish obey these rules. A clownfish moves among the tentacles with complete impunity, weaving through the same lethal forest that repels every other animal. It brushes against the tentacles repeatedly, even resting among them. Its body pressed directly against the armed surface. No harpoons fire. No toxins are released. The anemone remains still, its tentacles continuing their gentle motion as if nothing unusual is happening. This apparent contradiction is the result of a highly specific adaptation. Clownfish possess a specialized mucus layer on their skin that prevents nematocyst discharge. This coating masks the chemical signals that normally trigger firing, allowing physical contact without activation. The relationship is not innate at birth. Juvenile clownfish must acclimate carefully, making tentative contact and retreating repeatedly as they adjust their mucus composition. One mistake during this process can be fatal. But once established, the immunity is effective. This symbiosis benefits both partners. The clownfish gains protection from predators unwilling to brave the anemone's defenses. The anemone gains increased water circulation from the fish's movement, as well as nutrients from waste products and improved defense against some of its own predators. In this partnership, the anemone's weaponry becomes a shared fortress, selectively lethal to outsiders while welcoming a single trusted resident. For other animals, however, there is no such exemption. Shrimp, small fish, and drifting larvae that touch the tentacles are stung without discrimination. Even brief contact can cause lasting harm. The anemone does not assess size, species, or intent. Its response is purely mechanical and chemical. This lack of selectivity ensures reliability. The system cannot be tricked by speed or camouflage. If you touch it, you pay. Humans sometimes forget this. Sea anemones are often mistaken for harmless coral or decorative plants, their soft appearance inviting touch. When skin brushes against the tentacles, nematocysts fire just as they would against any other animal. The result is localized pain, irritation, and raised welts that can persist for hours or days depending on species and exposure. While most anemone stings are not life-threatening to humans, they are far from trivial. The sensation can be intense, and in sensitive individuals, systemic reactions are possible. This mismatch between appearance and function highlights a broader theme in marine ecosystems. Soft does not mean safe. Passive does not mean defenseless. Some of the most effective predators and defenders in the ocean do not move at all. They rely instead on proximity and inevitability, on the certainty that sooner or later something will make contact. From an ecological perspective, sea anemones occupy a unique role. They are both predator and structure, living hazards that alter the physical and behavioral landscape around them. Their presence can reduce local prey abundance, not only by direct capture, but by discouraging feeding in surrounding areas. This creates microhabitats where certain species thrive while others avoid, contributing to the patchwork diversity characteristic of healthy reefs. The automatic nature of nematocysts also represents a fundamental evolutionary solution to the problem of reaction time. In environments where milliseconds matter, removing the nervous system from the equation ensures maximum speed. The anemone does not sense and respond. It is always responding. The trigger is built into the contact itself. This eliminates delay and error, turning every tentacle into an extension of a reflex that never tires. Even predators that can tolerate mild stings tend to avoid repeated contact. Nematocyst toxins may not always kill, but they are effective at teaching. Pain, irritation, and temporary dysfunction are enough to discourage further attempts. Over time, this learning shapes predator behavior, reinforcing the anemone's role as a no-touch organism. Its success does not depend on eliminating all threats, only on making interaction unpleasant enough to be avoided. As water movement shifts and light angles change, the anemone continues its slow, rhythmic motion. Tentacles extend and retract slightly, sampling the passing current. Microscopic weapons lie in wait along every surface, armed and ready, indifferent to scale or identity. Around it the reef adjusts. Fish pass wide. Predators steer clear. Only the clownfish remains, darting confidently among the tentacles, a living exception to an otherwise absolute rule. The sea anemone does not chase its prey or confront its enemies. It does not need to. Its defense and its feeding strategy are the same thing, built into its skin and activated by touch alone. In a world of speed, teeth, and pursuit, the anemone proves that sometimes the most effective weapon is simply being impossible to touch safely. The reef floor changes character where sea urchins dominate. What was once open substrate becomes a low forest of spines, a field of rigid needles radiating outward from dark, compact bodies wedged into rock and crevice. Light fragments here, breaking into sharp contrasts as shadows fall between the spines. Fish approach these zones cautiously, slowing their patrols, circling rather than committing. Nothing about a sea urchin looks fast or aggressive, yet the hesitation around it is immediate and learned. This is not passive scenery. This is contested ground. A sea urchin does not flee danger. It cannot. Instead, it turns its entire body into a defensive surface. Hundreds, sometimes thousands of spines articulate independently, swiveling subtly to track approaching threats. From a distance they appear static, but up close their movement is unmistakable. When a fish drifts too near, the spines angle outward, increasing effective diameter and turning the urchin into a spiked sphere that is difficult to grasp from any angle. There is no single weak side. Every approach carries risk. The primary defense is mechanical. The spines are hard, sharp, and brittle in a way that favors the urchin. When pressure is applied, they puncture skin, fins, and mouths easily. But they do not always snap cleanly. Many break off inside the attacker, lodging fragments deep in tissue. For a predator, this is not just pain, it is impairment. A spine embedded in the mouth interferes with feeding. One in a fin affects maneuverability. Even a small injury can reduce hunting success, making the cost of an attempted bite higher than the reward. In some species, this mechanical threat is enhanced by chemistry. Venomous or irritating compounds coat the spines or are delivered by tiny pincer-like structures called pedicellariae that snap shut on contact. These toxins vary widely among species, but their function is consistent. They intensify pain, provoke inflammation, and discourage repeated contact. The sea urchin does not rely on venom alone, nor does it rely on spines alone. It layers defenses, ensuring that even predators capable of tolerating one aspect are challenged by another. This layered strategy reflects an evolutionary arms race played out over millions of years. Sea urchins are slow, conspicuous, and nutritionally dense. They are valuable prey. As a result, predators have repeatedly evolved ways to overcome their defenses. Some fish develop powerful jaws and specialized teeth capable of crushing spines and cracking the calcified shell beneath. Others attack from specific angles, flipping the urchin to expose the softer oral surface. Each innovation is met by counterpressure. Thicker spines, stronger toxins, more robust shells. The reef bears the scars of this conflict. Many urchins show broken spines, regrown unevenly or missing entirely, evidence of past encounters that neither side fully won. These injuries do not necessarily kill the urchin. It can regenerate spines over time, reallocating energy toward repair. This resilience ensures that even unsuccessful predation attempts impose lasting costs on predators without eliminating the urchin population. Survival here is not about perfection, but persistence. Fish that circle sea urchins often know exactly what they are looking at. They test distance carefully, approaching just close enough to gauge movement before backing away. Juvenile fish learn quickly, often after painful first encounters. The lesson spreads culturally within populations, reinforcing avoidance behaviors that reduce pressure on urchin communities. In this way, the presence of spines influences feeding routes and habitat use far beyond the immediate area. Yet the arms race does not stop there. Some predators become specialists. Triggerfish, for example, develop crushing dentition and problem-solving behaviors that allow them to pick up urchins, flip them, and strike vulnerable surfaces. They use repeated blows rather than single bites, minimizing exposure to spines. In coastal regions, sea otters add another layer of escalation. With dexterous paws and learned techniques, they use rocks as tools to crack open urchins, bypassing the spines entirely. These predators represent evolutionary answers to a defensive problem, not brute force solutions. When such specialists are present, the balance shifts again. Urchin populations may decline, allowing kelp and algae to flourish. When predators are removed, urchins can explode in number, overgrazing vegetation and transforming complex habitats into barren seascapes. This cascade reveals why the sea urchin's defenses matter beyond individual survival. They influence who eats whom, and therefore what entire ecosystems look like. The toxins associated with some urchins add another dimension to this balance. While not all species are venomous, those that are deliver chemical deterrents that complicate predation strategies further. Pedicellariae latch onto soft tissue, injecting irritants that cause pain disproportionate to the size of the animal. These structures are especially effective against small predators and scavengers that might otherwise probe around spines. The message is consistent. Contact is costly. Humans experience this cost directly. Sea urchins are often encountered in shallow water, where people wade, swim, or explore reefs casually. A misstep brings skin into direct contact with spines that puncture easily and break off beneath the surface. Removal is difficult, sometimes impossible without medical intervention. Embedded fragments can lead to prolonged pain, inflammation, and infection. The danger is not dramatic, but it is persistent. A single careless moment can lead to weeks of discomfort. This is why sea urchins are small but serious. They do not chase or attack. They simply exist as hazards, turning the substrate itself into a defensive zone. Their presence forces caution both in animals and humans, reshaping behavior through consequence rather than threat display. Over time, this shapes how reefs are used, which species dominate, and where energy flows. The arms race continues silently. Predators refine techniques. Urchins refine defenses. Neither side achieves permanent victory. Instead, equilibrium emerges, dynamic and conditional, dependent on who is present and how skilled they are. This ongoing pressure drives innovation on both sides, producing some of the most specialized feeding strategies and defensive structures in the marine world. As the light shifts and the reef settles into its steady rhythm, the sea urchin remains where it began, spines angled outward, surface bristling with readiness. Fish continue to circle, measuring risk against hunger. Somewhere nearby, a specialist predator may be watching, calculating angles and timing. The outcome is never guaranteed. What is certain is that the defenses do not end predation. They shape it. They force predators to become smarter, stronger, or more inventive, ensuring that survival here is earned, not given. In this way, the sea urchin stands as a quiet architect of evolution. Its spines and toxins do not merely protect a single animal. They sculpt behaviors, select for intelligence and strength, and drive the relentless escalation that defines life on the reef. The battle is not loud or fast, but it is constant, written into every broken spine and every cautious approach. The seafloor looks calm at this depth, almost slow in the way only benthic worlds can be. Sand settles gently between scattered rocks and coral rubble, and life here moves with deliberate restraint. A sea cucumber crawls across this terrain inch by inch, its body elongated and soft, pressing against the substrate as rows of tiny tube feet grip, release, and grip again. There is no hurry in its movement. Nothing about its shape suggests danger. It resembles a misplaced vegetable more than an animal, a flexible cylinder absorbing the rhythm of the current as it feeds on organic debris embedded in the sand. This apparent vulnerability is deceptive. In ecosystems where speed and armor dominate survival narratives, the sea cucumber represents a different solution entirely. It survives not by outrunning predators or resisting bites, but by rewriting what an attack feels like. When threatened, it does not fight back in the traditional sense. It turns the encounter into a chemical and physical nightmare for anything foolish enough to press the attack. A predatory fish drifts closer, curious rather than committed. It circles, assessing texture and movement, testing whether this slow, unprotected body is worth the effort. Sea cucumbers are nutrient-rich, packed with protein and easily swallowed by larger mouths. Many predators have evolved to exploit soft-bodied prey precisely because they lack spines or shells. The fish nudges closer, snout brushing the cucumber's surface. There is still no response. The cucumber continues its crawl, unreactive, almost indifferent. Then pressure increases. The predator bites. What follows is not a chase or a struggle, but an eruption. From the posterior end of the sea cucumber, long white threads explode outward into the water column, unfurling with shocking speed. These are Cuvierian tubules, specialized internal organs stored tightly coiled inside the body until needed. Once expelled, they stretch rapidly, becoming sticky, elastic filaments that adhere to anything they touch. The predator recoils instantly, but it is already too late. The tubules cling to the fish's mouth, gills and fins, wrapping around delicate structures like wet threads of glue soaked in irritation. Movement becomes awkward. Each attempt to pull away only stretches the filaments further, increasing entanglement. At the same time, chemical compounds embedded in the tubules and body tissues diffuse into the surrounding water, intensifying the deterrent. This is not venom meant to kill. It is a sensory overload designed to disgust, distract, and disable long enough for survival to be secured. The toxins involved are often saponins, soap-like molecules that disrupt cell membranes and irritate exposed tissues. In fish, they inflame gills, interfere with respiration, and create an immediate sensation of distress. Combined with the physical obstruction of sticky filaments, this turns a simple predation attempt into a chaotic retreat. The predator thrashes briefly, then bolts, desperate to escape the source of irritation. The sea cucumber remains behind, torn and exposed, but alive. This strategy works because it does not require precision. The cucumber does not need to aim or time an attack. The tubules deploy automatically under stress, triggered by mechanical pressure or chemical cues associated with injury. Like a smoke bomb combined with a net, the response creates confusion rather than confrontation. In the benthic world, where escape options are limited and bodies are slow, buying time is often enough. The cost of this defense is significant. Ejecting Cuvierian tubules means sacrificing part of the body. These structures are torn free during deployment, leaving the cucumber temporarily depleted and vulnerable. Regeneration takes time and energy, sometimes weeks. During this period, the animal relies on remaining chemical defenses and reduced activity to avoid further encounters. Yet the trade-off is worth it. A predator that experiences this defense once is unlikely to repeat the mistake. Not all sea cucumbers possess Cuvierian tubules, but many species compensate with higher concentrations of toxins in their tissues. These chemicals make the body unpalatable or actively harmful to consume. Predators that ingest parts of a toxic sea cucumber may experience muscle weakness, impaired coordination, or internal irritation that discourages further feeding. In some reef systems, this toxicity is strong enough that fish learn to avoid the distinctive silhouette of sea cucumbers entirely, associating their shape with negative consequences. This learning effect reshapes benthic ecosystems. Areas dense with sea cucumbers become lower risk zones for other slow-moving invertebrates that benefit indirectly from predator avoidance. At the same time, specialized predators evolve to handle or tolerate these defenses. Some species attack selectively, biting off small portions rather than attempting to consume the entire animal. Others target less toxic species or juveniles that have not yet accumulated chemical defenses. The arms race continues, not through escalation of speed or armor, but through refinement of chemistry and behavior. For humans, sea cucumbers are rarely dangerous in everyday encounters, but they are not harmless curiosities. Contact with expelled tubules can cause skin irritation, and handling some species improperly can expose people to toxins that inflame eyes, mucous membranes, or wounds. In confined spaces, such as tide pools or aquaria, the release of toxins can even affect nearby fish, underscoring how potent these compounds can be despite the animal's passive appearance. The danger is situational rather than aggressive, rooted in stress responses rather than intent. What makes the sea cucumber's defense especially remarkable is how it transforms weakness into leverage. Soft tissue, which would normally invite predation, becomes the delivery system for chemical deterrence. Lack of mobility, which would usually spell doom, is offset by defenses that activate at the moment of contact. The sea cucumber does not need to escape quickly because it ensures that attackers want to escape from it. This strategy reflects a broader pattern in marine evolution. Not all successful animals are built to fight. Some are built to make fighting unpleasant. By turning itself into an experience predators regret, the sea cucumber secures its place in the ecosystem without ever appearing threatening. Its survival depends on reputation as much as physiology, on the memory of past encounters carried by fish that learned the cost of curiosity. After the attack, the cucumber resumes its slow crawl, damaged but functioning. The tubules left behind drift and degrade, eventually consumed or broken down by scavengers. Over time, new structures will regenerate inside the body, restoring the defensive arsenal. The incident leaves no permanent mark on the landscape, but it reinforces the invisible rules governing it. Soft does not mean defenseless. Slow does not mean helpless. In the grand architecture of the reef, sea cucumbers play multiple roles. They recycle nutrients by processing sediment, oxygenating the seabed, and supporting microbial communities essential to reef health. Their defenses ensure they can perform this ecological work without being eliminated by predators. By surviving, they maintain the balance between consumption and regeneration that keeps benthic systems functioning. The toxic smoke bomb and sticky trap are not dramatic weapons. They do not kill quickly or decisively. Instead, they create space, confusion, and discomfort. They buy survival through chemistry and inconvenience rather than force. In doing so, They demonstrate that evolution does not favor strength alone. It favors solutions that work within constraints. As the water settles and the reef returns to its steady rhythm, the sea cucumber continues its unremarkable journey across the sand. Few animals notice it. Fewer still challenge it. Beneath its soft exterior lies a system finely tuned to discourage violence, a reminder that in the ocean, even the most defenseless-looking creatures can carry consequences that turn predators away. The reef floor flashes with color where logic says it should not. Against muted sand and weathered coral, a sea slug crawls openly, its body painted in electric blues, oranges, and yellows so vivid they seem almost artificial. It does not hide. It does not rush. Its movement is slow, deliberate, exposed. For a creature with no shell, no speed, and no visible weaponry, this confidence looks like a mistake. In the open ocean, being bright and slow usually means being eaten. Here, it means something very different. This is a nudibranch, a sea slug that has abandoned the traditional defenses of mollusks and replaced them with something far stranger. Its body is soft and vulnerable, its skin thin enough to show internal structures beneath. Yet predators hesitate. Fish approach, pause, and turn away. The slug continues forward, unconcerned, its frilled appendages rippling gently in the current like decorative fins. This is not ignorance of danger. This is informed boldness. The warning is written directly onto the body. Bright coloration in marine environments often signals toxicity, a message learned quickly by predators that survive their first mistake. In the case of many sea slugs, that message is honest. These animals are not just distasteful. They are chemically armed, carrying poisons powerful enough to burn mouths, irritate gills, or disrupt basic physiology. The shocking part is how they acquired them. Unlike animals that manufacture venom through specialized glands, many sea slugs do not synthesize their own toxins at all. They steal them. The slug moves across the surface of its prey, which may be a toxic sponge, a hydroid colony, or even a venomous sea anemone. Its feeding is precise and selective, rasping away tissue with a specialized radula while avoiding damage to itself. As it consumes this toxic meal, the slug's body does something extraordinary. Instead of breaking down the poisons, it isolates and stores them, transporting chemical compounds intact through its digestive system and into specialized tissues where they can be redeployed for defense. This process is known as sequestration, and it turns the food web upside down. The prey's chemical defenses, evolved to deter predators, are repurposed by the slug into a portable arsenal. The slug becomes dangerous not because of what it is, but because of what it has eaten. Change the diet, and the weapon changes too. In some groups, this theft goes even further. Certain nudibranches that feed on stinging animals such as hydroids or anemones do not merely steal toxins, they steal the weapons themselves. Undischarged nematocysts, the microscopic harpoons used by cnidarians to sting prey, pass unharmed through the slug's digestive tract. Instead of firing, they are transported to the tips of finger-like structures called serrata that line the slug's back. There, they are stored, intact and functional, ready to fire when a predator makes contact. This is not mimicry. This is armed robbery at a cellular level. When a fish bites one of these slugs, the serrata rupture, releasing both stolen toxins and borrowed stinging cells directly into the attacker's mouth. The effect is immediate. Pain, irritation, and shock trigger rapid rejection. The fish spits the slug out, sometimes violently, shaking its head as it retreats. The slug survives the encounter damaged but alive, and the predator learns a lesson it will not repeat soon. This system depends on extraordinary biological precision. The slug must prevent the nematocysts from firing while transporting them, a feat achieved through specialized tissues and mucus that inhibit discharge. Once positioned in the serrata, the stinging cells are exposed to conditions that allow activation upon contact with predator tissue. The slug has turned its back into a minefield, one that is rebuilt continuously as it feeds. The serrata themselves serve multiple roles. They increase surface area for respiration, allowing gas exchange directly through the skin. They store stolen defenses. They can even be sacrificed. If a predator bites off a cerus, it breaks away easily, distracting the attacker while delivering a chemical payload. The slug continues crawling, wounded but not dead, capable of regenerating lost appendages over time. This strategy works only because of the slug's honesty. The bright colors are not decorative, they are advertisements. In evolutionary terms, this is aposematism, the use of conspicuous signals to warn predators of danger. Predators that ignore the warning once rarely do so again. Over time, entire communities learn to associate certain color patterns with negative outcomes. This learned avoidance creates a shield around the slug that extends far beyond any single individual. The reef adjusts accordingly. Fish alter their foraging routes. Juveniles learn from failed attacks or from watching others recoil. The presence of chemically defended slugs reshapes microhabitats, creating pockets where predation pressure is lower. Other vulnerable species may benefit indirectly, sharing space with animals predators have learned to avoid. In this way, a slow, crawling mollusk influences the behavior of faster, stronger animals simply by existing visibly and honestly. For humans, the risk posed by sea slugs is usually limited but real. Most are not dangerous unless handled, but skin contact with certain species can cause irritation or burning sensations. The danger lies in assumption. Their soft appearance invites touch, especially given their striking colors. But those colors are warnings, not invitations. The safest rule underwater remains simple. Do not touch unfamiliar organisms, especially those that seem to be advertising themselves. What makes the sea slug's strategy so remarkable is how it bypasses traditional evolutionary constraints. Building venom glands is expensive. Maintaining armor requires calcium and energy. Speed demands muscle and oxygen. The slug invests in none of these. Instead, it lets other species do the hard work, then appropriates the results. It turns the reef's chemical diversity into a modular defense system, changing loadouts by changing diet. This creates incredible diversity among sea slugs. Two species may look similar, but carry entirely different toxins depending on what they consume. Even within a single species, individuals from different habitats may vary in toxicity. Predators cannot rely solely on species recognition. They must learn locally through experience, reinforcing the power of warning coloration and learned avoidance. From an evolutionary perspective, this is theft refined into survival. The slug does not innovate new weapons. It hijacks existing ones and deploys them in a new context. This reduces evolutionary cost while increasing effectiveness, a rare combination. It also creates dependence. Remove the toxic prey from the environment, and the slug loses its primary defense. This ties its fate tightly to the health and composition of the reef community. That dependency reveals deeper ecological connections. Sea slugs are not isolated curiosities. They are indicators of chemical pathways moving through the ecosystem. Their presence reflects the availability of toxic prey species, the stability of reef microhabitats, and the balance of predator learning. In some systems, declines in chemically defended prey lead directly to declines in slugs that depend on them, with cascading effects on predator behavior and reef structure. As the slug continues its slow progress across the substrate, its colors pulse against the blue water, impossible to ignore. It leaves no trail of destruction, no sign of aggression. Yet everything about it communicates consequence. Predators see it and remember. Humans see it and should pause. This animal is not protected by speed or strength, but by intelligence encoded in behavior and physiology, by the ability to recognize danger in others and turn it into armor. In the ocean, not all weapons are built. Some are borrowed, some are stolen, and some of the most effective defenses belong to animals that look, at first glance, utterly defenseless. The sea slug proves that survival does not always go to the strongest or fastest. Sometimes it goes to the thief who knows exactly what to take and how to wear it openly without fear. The seafloor tightens around an outcrop of rock where shadows pool and movement slows. Here, beneath ledges and inside narrow cavities, chaos is inefficient. Speed is useless. Teeth have no room to swing. Anything that hunts in this space must solve a different problem, not how to chase, but how to control. From the darkness, an octopus unfolds. At first it is only a suggestion, a shift in texture against stone. Skin darkens to match the rock, then ripples as 8 arms extend outward, each one moving with independent intent. Suckers taste the water, sampling chemical traces left by passing animals, reading the history of the crevice like a map written in molecules. Somewhere nearby, a crab picks its way across the substrate, claws clicking softly as it tests the ground. The octopus does not rush. It never does. When the strike comes, it is total. Arms surge forward in a coordinated collapse of space, wrapping around the crab from every angle at once. Suckers lock down, hundreds of them forming a living net that eliminates leverage, escape, and orientation in a single instant. This is not a chase. This is containment. The crab thrashes, claws scraping uselessly against flesh that behaves like muscle and mind combined. The octopus adjusts grip pressure automatically, tightening where resistance spikes, relaxing where it does not. Within seconds, the prey is immobilized, pinned against rock by intelligence rather than force. Only then does the venom enter the equation. At the center of the octopus's arms, a hard beak presses forward, finding a precise point between plates of armor. The bite is small, surgical, delivered exactly where it needs to be. Saliva flows into the wound, carrying venom produced in specialized salivary glands. This venom is not designed for spectacle. It does not burn or explode through tissue. It works quietly, targeting neuromuscular systems, disrupting signal transmission, and accelerating collapse. Muscles weaken. Coordination fails. The struggle ends not because the prey is torn apart, but because it simply stops working. This combination of restraint and chemistry is what makes octopus venom different. Many venomous animals rely on speed to avoid retaliation, delivering a quick dose and retreating. The octopus does the opposite. It commits fully, using its arms to remove uncertainty before the venom ever acts. There is no chaos, no flailing, no risk of injury from claws or spines. The venom has time to work because the prey has nowhere to go. This approach reflects the octopus's broader strategy as a predator. It does not compete in open water. It does not pursue fish across distance or overwhelm prey through brute strength. Instead, it engineers situations where escape is physically impossible. The arms are not just tools of capture. They are sensory organs, decision makers, and adaptive restraints that respond faster than centralized thought. Each sucker contains its own neural network, allowing the arms to make local decisions in real time. The result is a predator that controls space rather than chasing movement. The venom itself serves multiple purposes. In addition to immobilizing prey, it begins the process of digestion before feeding truly starts. Enzymatic components break down tissue, softening muscle and connective structures, making consumption easier and more efficient. This is external digestion paired with paralysis, a way to turn a hard, armored animal into a manageable meal without prolonged effort. For crustaceans like crabs and lobsters, this is especially effective. Their shells remain intact while the inside is rendered unusable. Once the prey goes limp, the octopus relaxes its grip slightly, not out of mercy but efficiency. Feeding begins calmly. There is no urgency now. The kill is complete, even though the prey may still be alive in a biological sense. Control has replaced violence. The octopus eats at its own pace, secure in the knowledge that resistance is over. This method scales across prey types. Fish caught by octopuses experience a similar sequence, though restraint dynamics differ. Arms pin fins and gills, preventing propulsion, while venom weakens muscle tone and coordination. Fish that rely on explosive movement to escape suddenly find their bodies refusing to respond. Panic is replaced by inertia. In the confined spaces octopuses prefer, that shift is fatal. Humans are rarely targets in this system, but the mechanism still applies. Most octopus bites occur during handling, either accidental or intentional, when the animal feels threatened. The bite is usually defensive, not predatory, and the amount of venom delivered is small. Pain, swelling, and irritation are common outcomes. In a few species, the venom is medically significant and can cause more serious symptoms, but encounters remain rare. The important distinction is intent. The octopus does not hunt humans. It defends itself when control is challenged. What sets the octopus apart from other venomous animals is not toxicity, but discretion. Venom is not its primary weapon. Intelligence is. The octopus decides when venom is necessary and how much to use. It chooses targets based on vulnerability, environment, and risk. It avoids unnecessary conflict. It retreats when conditions are unfavorable. This selectivity is rare in invertebrates and reveals how deeply cognition is embedded in octopus behavior. That intelligence extends beyond hunting. Octopuses are known to manipulate objects, use tools, and modify their environment to create safer hunting and resting spaces. Some species collect shells or debris to build temporary shelters. Others plug den entrances with rocks when threatened. These behaviors reduce reliance on venom by minimizing exposure to danger. Venom becomes a backup plan rather than a default response. From an evolutionary standpoint, this is a sophisticated solution. Venom production is energetically expensive. Using it indiscriminately would be wasteful. By pairing venom with physical control and decision-making, octopuses maximize return on investment. Every dose is delivered under optimal conditions, increasing success while minimizing cost. The impact of this strategy on ecosystems is subtle but significant. Octopuses regulate populations of crustaceans and small fish, often targeting individuals that shelter in complex structures inaccessible to other predators. This prevents certain prey species from dominating reef crevices and benthic zones, maintaining diversity. Because octopuses hunt selectively and intermittently, their influence is more surgical than sweeping, shaping communities without destabilizing them. The reef responds accordingly. Crabs alter movement patterns, becoming more cautious around narrow openings. Fish avoid certain textures and shapes associated with octopus dens. These behavioral shifts ripple outward, influencing feeding times, habitat use, and even reproductive strategies. The octopus does not need to be abundant to matter. Its presence alone is enough to change how other animals behave. As feeding ends, the octopus withdraws, arms folding back into shadow. Skin texture smooths, color fades to match surrounding stone. Within moments, it is gone, leaving behind nothing but fragments of shell and the memory of control imposed with perfect timing. There is no sign of struggle, no evidence of violence beyond the absence of life where it once moved. This is the octopus's signature. It does not dominate through speed or strength. It dominates through precision, patience, and restraint. Venom is part of the equation, but never the whole story. The real weapon is the ability to remove chaos from a fight before it begins, to decide the outcome in advance by controlling every variable that matters. In the ocean, where many predators rely on overwhelming force, the octopus represents a different lineage of success. It shows that intelligence paired with chemistry can outperform speed, that control can replace pursuit, and that the most efficient kills are often the quietest. The seafloor here looks exposed, almost unfinished. Fine sand stretches between scattered bits of shell and rubble, interrupted only by shallow burrows and low coral outcrops that offer little true shelter. In this open space, most animals move quickly or not at all. To hesitate is to be seen, and to be seen is to be eaten. Yet something moves across the sand without urgency, its body changing shape as it goes, never settling into a single form long enough to be defined. At first it resembles a small flounder, body flattened and gliding low, arms pulled tight to create a smooth diamond-shaped silhouette that skims just above the bottom. Then the shape loosens. The body lifts, elongates, and suddenly what looked like a fish becomes something else entirely. Two arms trail behind like a ribbon, banded in stark black and white, undulating with the precise rhythm of a sea snake. A moment later, the posture shifts again. Arms flare outward in a slow, deliberate spread, spines implied by posture alone, evoking the unmistakable outline of a lionfish drifting confidently through open water. This is the mimic octopus, and its most powerful weapon is not venom, speed, or strength. It is doubt. Unlike many octopus species that rely primarily on camouflage to disappear, the mimic octopus often chooses the opposite strategy. It makes itself obvious, but never predictable. Its body becomes a moving catalogue of danger, borrowing the shapes, motions, and warning signals of some of the most avoided animals in the reef. It does not merely resemble them in color. It copies posture, behavior, and timing with uncanny accuracy, enough to trigger learned avoidance responses in fish that have survived past encounters with truly dangerous species. The key here is that the mimic octopus does not need to be poisonous. It needs others to believe it might be. Predators approaching from a distance see a silhouette they recognize, and recognition carries memory. A banded sea snake means venom and paralysis. A lionfish outline means needles and pain. A flounder shape suggests a fast burst escape followed by buried camouflage. Each of these forms carries a cost associated with getting too close. The mimic octopus exploits this mental shortcut relentlessly, switching identities mid-movement as conditions change. This shape-shifting is not random. It is context-dependent and selective. When crossing open sand with few hiding places, the octopus adopts the appearance of venomous animals that patrol exposed terrain. When slipping toward burrows or crevices, it elongates its arms and compresses its body into an eel-like form, sliding into holes that would otherwise seem occupied by something dangerous. Prey fish hesitate to enter these spaces, unwilling to challenge what looks like a resident predator. That hesitation is often enough. In the shallow waters where mimic octopuses live, hesitation is lethal currency. A fraction of a second determines whether a fish flees, freezes, or is caught. By manipulating perception rather than reality, the mimic octopus buys time without expending energy. It does not chase. It does not sprint. It waits for the moment when prey pauses, uncertain, then collapses the distance with sudden precision. The mechanics behind this ability are rooted in the octopus's extraordinary control over its body. With no internal skeleton, it can reshape itself freely, redistributing muscle tension and changing posture instantly. Specialized skin cells allow rapid color and pattern changes, but the mimic octopus often relies more on shape and motion than pigmentation alone. The illusion works because predators respond first to silhouette and behavior, not fine detail. The octopus understands this instinctively, using broad visual cues to influence decisions made in milliseconds. What makes this strategy especially powerful is that it operates in both directions. Prey hesitate because they fear danger. Predators hesitate because they fear injury. In both cases, the mimic octopus benefits. It can hunt in areas where a normal octopus would be too exposed, and it can escape encounters that would otherwise require ink release or frantic flight. The borrowed danger becomes a movable shield. This is not true mimicry in the evolutionary sense of resembling a single model species consistently. It is dynamic deception, an adaptive performance shaped moment to moment by environmental context. The octopus assesses what animals are present, what threats are likely, and which illusion will be most effective. In some observations, individuals have been seen switching between multiple mimicked forms within a single encounter, adjusting as different fish respond differently. The effectiveness of this strategy depends on a crucial assumption. The reef must already be dangerous. Mimicry only works in communities where predators have learned hard lessons. A fish that has never encountered a sea snake will not fear a snake-like silhouette. A predator unfamiliar with lionfish will not respect a flared fin display. The mimic octopus thrives in ecosystems rich with genuine threats, piggybacking on the reputations of others. This reveals an underappreciated layer of reef warfare. Chemical defenses are not the only forces shaping behavior. Memory, learning, and pattern recognition play equally powerful roles. Animals do not react solely to what something is, but to what it resembles. The mimic octopus turns this cognitive shortcut into a survival strategy. There is no venom involved in this deception. The octopus's bite does contain venom, like other octopus species, But that is not the focus here. The goal is to avoid bites altogether, to control encounters before contact happens. When physical interaction does occur, the mimic octopus still relies on arms, intelligence, and restraint rather than chemical force. The deception simply reduces how often those tools are needed. For prey fish, this creates a complex decision landscape. Approaching a burrow might mean safety, or it might mean a snake. Investigating a drifting shape could reveal a harmless animal, or it could be a lionfish analog with imagined spines. Over time, prey become more cautious, slowing feeding rates and altering movement patterns in areas frequented by mimics. This reshapes energy flow across sandy habitats that might otherwise be heavily grazed. Predators face similar dilemmas. Attacking the wrong silhouette can result in pain, paralysis, or lost hunting ability. Even a false alarm carries cost. Every aborted strike is wasted energy. As a result, predators become conservative, avoiding anything that triggers uncertainty. The mimic octopus thrives in this zone of ambiguity, where doubt is safer than certainty. Humans rarely notice this warfare playing out beneath their feet. Mimic octopuses live in shallow coastal environments, often near shorelines where people wade, snorkel, or walk along sandy bottoms. They are not aggressive and pose little direct threat, but their presence underscores how sophisticated deception can be, even in seemingly simple habitats. The sand flats are not empty. They are arenas of perception and misdirection. From an evolutionary perspective, this strategy is expensive in one way and efficient in another. Maintaining the neural complexity required for rapid behavioral assessment and body control demands energy. The brain of an octopus is among the most developed of any invertebrate, but this cost is offset by reduced need for armor, speed, or frequent chemical defense deployment. The octopus does not need to regenerate spines or replenish toxins. It needs only to think faster than its enemies. This reliance on cognition blurs the line between physical and psychological warfare. The reef is not just a battleground of teeth and venom, it is a network of expectations. Animals survive not only by what they can do, but by what others believe they can do. The mimic octopus weaponizes belief. As it moves across the sand, the octopus pauses, then flattens again, gliding like a ray for several body lengths before melting into a ripple of arms that vanish into a burrow. No ink, no chase, no visible threat. Only the lingering sense that something dangerous was just present, even if nothing physically harmful occurred. This is why the mimic octopus matters. It reveals that survival in the ocean is not governed solely by chemistry or muscle. It is governed by decision-making under uncertainty. Animals constantly evaluate risk with incomplete information. Those that can manipulate that process gain disproportionate power. The mimic octopus does not need to win fights. It only needs to prevent them. By borrowing danger rather than evolving it, it sidesteps the costs of toxicity while reaping many of the benefits. In doing so, it exposes a deeper truth about life on the reef. Sometimes the most effective weapon is not poison in the blood or spines on the skin, but fear placed carefully in the mind of another animal. As the tide shifts and the light changes, the sand flats return to their quiet rhythm. Fish resume feeding. Predators patrol the edges. Somewhere beneath the surface, an octopus changes shape again, preparing its next performance. The reef remains dangerous, but not always in the ways it appears. The open water feels endless until something moves fast enough to redraw it. A squid cuts across the blue, mantle flexing in powerful pulses as fins flare and collapse along its sides. Each jet of water expelled from its siphon carries it forward in a sudden burst, then silence, then another burst, a rhythm tuned for escape rather than endurance. Behind it, a predator accelerates, body narrowing, eyes fixed. In open water, there are few places to hide, and pursuit here usually ends one way. Then the water darkens. A cloud blooms where the squid was a heartbeat earlier, spreading outward in an expanding plume that looks solid enough to grab. The predator does exactly that, striking into the darkness with precision, honed by countless successful chases. But there is nothing there. The squid is already gone, veering sharply away. mantle contracting in a new direction as the cloud continues to billow and drift. What the predator attacked was not the squid, but a chemical lie. Squid ink is often described as a visual trick, a smokescreen that blocks sight long enough for escape. That is true, but incomplete. Ink is not just pigment released into water. It is a complex chemical tool designed not only to hide the squid, but to interfere with how predators think, see, and track. In this sense, ink is not poison, but it is weaponized chemistry all the same. The ink originates in a specialized sac connected to the squid's digestive system, a structure that has evolved specifically for emergency release. When threatened, muscles around the sac contract, forcing ink through a duct and out into the surrounding water, often mixed with mucus, to give it texture and persistence. The result is not always a simple cloud. In many cases, the ink forms a pseudomorph, a dense, roughly squid-shaped mass that hangs together just long enough to be convincing. Predators do not simply lose sight of the squid. They are given something else to focus on. Vision is only part of the story. Many fish and marine predators rely heavily on chemical cues to track prey, following scent gradients and disturbance signals left behind by movement. Squid ink interferes with this process. The ink contains compounds that irritate sensory receptors and overwhelm chemosensory systems, creating a burst of information that masks the squid's true trail. Instead of a clear signal pointing forward, the predator encounters noise, confusion, and contradiction. This matters because pursuit in open water depends on continuity. A predator locks onto a target and commits energy to the chase, making split-second adjustments based on visual and chemical feedback. Break that feedback loop, and the chase collapses. The predator must reassess, slow down, and search again. In that moment of hesitation, the squid escapes. The chemistry of ink varies among species, but common components include melanin, the pigment responsible for its dark color, as well as amino acids and other compounds that interact with sensory systems. In some predators, ink has been shown to reduce feeding responses temporarily, dampening appetite or disrupting normal behavioral patterns. This is not incapacitation. It is interference. The goal is not to harm the predator, but to make it hesitate. The effectiveness of this strategy depends on timing and placement. Squid do not release ink randomly. The cloud is often expelled at the precise moment the predator commits to an attack, maximizing the chance that the predator will strike the decoy rather than the real animal. At the same time, the squid changes direction, using powerful jets to create distance while the predator is momentarily occupied. The escape is not blind panic. It is a coordinated maneuver that combines chemistry, physics, and behavior. This is especially important because squid are built for speed, not defense. They have no shells, no spines, no venomous bite to deter attackers. Their bodies are soft and vulnerable, optimized for rapid movement and precise control rather than durability. Ink allows them to survive in open water where hiding places are scarce and encounters are sudden. The pseudomorph effect illustrates how sophisticated this defense can be. Instead of dispersing immediately, the ink forms a cohesive shape that lingers, maintaining enough structure to resemble a living animal. Predators strike it instinctively, guided by shape recognition and movement patterns. Even experienced hunters can be fooled, because the decoy exploits the same sensory shortcuts they use to catch real prey. Once the predator realizes the mistake, it is already too late. The squid has altered its trajectory, often angling upward or downward into layers of water with different light conditions, further complicating tracking. The ink cloud, meanwhile, continues to expand and dissipate, erasing the last reliable clues. This strategy is not limited to one type of predator. Fish, marine mammals, and even humans respond instinctively to sudden visual obstructions and sensory overload. Divers who encounter ink clouds describe momentary disorientation, reduced visibility, and a sense of confusion as the dark plume spreads. While ink poses little direct danger to humans, its ability to disrupt perception is undeniable. From an ecological perspective, ink shapes predator-prey dynamics in subtle ways. predators that frequently encounter inking squid may adjust hunting strategies, learning to anticipate direction changes or delay strikes until after ink release. Squid, in turn, refine timing and release patterns, creating an ongoing evolutionary dialogue between hunter and hunted. This is not an arms race of sharper teeth or thicker armor, but of better deception and better interpretation. Ink also allows squid to inhabit ecological niches that would otherwise be too risky. Many species occupy mid-water zones where cover is minimal and encounters are frequent. Without ink, survival rates would plummet. With it, squid can afford to forage, migrate, and reproduce in open environments, contributing significantly to marine food webs as both predator and prey. Their role as prey is especially important. Squid are a major food source for a wide range of animals, from fish to whales. Ink does not eliminate predation. It filters it. Only the fastest, most persistent, or most adaptable predators succeed consistently. This selective pressure influences predator behavior and physiology, favoring those capable of coping with sensory disruption. At the same time, squid remain active hunters themselves, feeding on fish and invertebrates. Ink allows them to escape larger threats without compromising their own predatory effectiveness. It preserves their place in the ecosystem as agile, intelligent intermediaries between lower and higher trophic levels. The human angle here is subtle but instructive. Squid ink has been harvested and used for centuries, valued for its pigment and culinary properties. Yet its original purpose has nothing to do with art or flavor. It exists to manipulate perception, to create absence where presence was expected. In this sense, ink is a reminder that chemical warfare in nature does not always involve pain or paralysis. Sometimes it involves erasure. As the predator abandons the empty cloud and resumes its patrol, the water clears gradually. Light returns. The illusion fades. Somewhere beyond the edge of visibility, the squid slows its jets, mantle relaxing as it blends back into the blue. The encounter leaves no obvious trace. No injury, no remains. Only the outcome matters. The squid is alive. This is why ink matters. It demonstrates that survival is not always about overpowering an enemy. It can be about controlling information, about deciding what the predator perceives in the critical moment. By inserting false signals into the environment, the squid rewrites the rules of engagement. The predator does not lose because it is weak. It loses because it was misled. In the broader story of chemical defenses, squid ink occupies a unique position. It is not venom. It does not punish contact. It does not kill or incapacitate. Instead, it buys time, space, and opportunity by disrupting the mental map predators rely on. In doing so, it shows that chemistry can be used not just to harm, but to confuse. The open ocean remains dangerous, vast, and unforgiving. But as long as squid can turn water into darkness and certainty into doubt, they will continue to carve out a living in its most exposed spaces. Not all chemical weapons end lives. Some simply make you disappear. The water above the reef shimmers with clarity, sunlight folding into soft ripples that drift across sand and coral like slow breathing. In this open space, visibility is a double-edged reality. To be seen is to be targeted. And most hunters here rely on either speed or surprise to survive. Yet drifting just above the substrate is an animal that seems almost indifferent to exposure, hovering in full view, body outlined cleanly against the blue. A cuttlefish hangs motionless, fins rippling gently along its sides, eyes locked forward with an intensity that suggests calculation rather than fear. At first glance, it looks defenseless. Its body is broad and soft, lacking the obvious armor of shells or spines. It does not flee when fish pass nearby. It does not bury itself or retreat into cover. Instead, its skin begins to change. Bands of black and white ripple across its body in crisp, high-contrast waves, pulsing outward in rhythmic flashes that feel deliberate rather than reactive. The patterns are sharp, almost unnatural, cutting against the softer tones of the reef. For nearby fish, these displays are impossible to ignore. Movement slows. orientation falters. What was a casual patrol becomes hesitation. The cuttlefish is not using poison, and it is not mimicking a specific toxic animal. What it projects is danger without chemistry, a visual language that exploits the way prey process information. High contrast patterns trigger attention and confusion simultaneously, overwhelming the sensory filters fish rely on to detect motion and escape routes. The display does not need to mean anything specific. It only needs to interrupt decision-making. This is the cuttlefish's real weapon. Not venom, not speed, control. Cuttlefish possess one of the most sophisticated visual systems in the ocean, paired with skin capable of extraordinary transformation. Millions of specialized cells called chromatophores, iridophores and leucophores work together to change color, brightness and pattern in fractions of a second. Unlike simple camouflage, these changes are not limited to blending in. They can create illusions of movement, depth and shape that do not actually exist. The flashing patterns serve multiple purposes. To predators, they can signal alertness or unpredictability, discouraging approach. To prey, they function as a form of visual interference, masking the precise position of the cuttlefish's body while drawing attention to the display itself. The prey sees motion, contrast and threat, but not trajectory. While the display unfolds, the cuttlefish remains perfectly still. Then the strike happens. Two feeding tentacles shoot forward with explosive speed, extending far beyond the length of the body in a blink. The movement is so fast it is often invisible to the naked eye. One moment the prey hovers, uncertain. The next it is gone, snapped backward by suction cups at the tips of the tentacles that lock onto flesh with precision. The tentacles retract instantly, pulling the prey into the waiting arms where it is secured and subdued. There is no chase, no pursuit, no second chance. This capture method allows the cuttlefish to hunt in open water where ambush predators would struggle. Speed is concentrated into a single moment rather than sustained effort. Energy expenditure is minimal. Risk is controlled. The prey never reaches full escape velocity because it never realizes escape is necessary until too late. This hunting style depends on timing, perception, and neurological control. The cuttlefish must read distance accurately, predict prey movement, and coordinate skin display with muscle action flawlessly. Mistiming the tentacle strike by a fraction of a second results in failure. Yet cuttlefish succeed with remarkable consistency, a testament to how deeply integrated their sensory and motor systems are. What makes this strategy particularly effective is that it bypasses many common prey defenses. Fast-swimming fish rely on early detection and rapid acceleration. Schooling fish depend on coordinated movement and confusion effects. The cuttlefish short-circuits both. The display isolates attention. The strike ends the encounter before group dynamics or speed matter. This creates an unusual predator profile. The cuttlefish is not built to overpower large prey or endure prolonged conflict. Instead, it specializes in precision kills that leave little evidence behind. Shell fragments or scales may settle to the bottom, but the act itself is clean and quiet. From an ecological perspective, this places cuttlefish in a unique niche. They are visual predators that shape prey behavior through fear and uncertainty rather than persistent pressure. Fish that share habitats with cuttlefish learn to recognize certain patterns as dangerous, adjusting movement and spacing accordingly. Over time, this alters feeding routes and microhabitat use, subtly reshaping reef dynamics. Unlike chemical defenses that persist after contact, the cuttlefish's weapon exists only in the moment. Once the display ends, there is no lingering toxin or physical barrier. This makes cuttlefish encounters highly situational. The animal must remain alert, constantly reading its surroundings and deciding when to display, when to hide, and when to strike. This cognitive load is supported by one of the most advanced nervous systems among invertebrates. Cuttlefish brains are large relative to body size and capable of complex processing, learning, and memory. They can adapt hunting strategies based on experience, choosing different display patterns for different prey types and environments. Some patterns are more effective in open sand. Others work better against rocky backgrounds. The cuttlefish adjusts accordingly. This adaptability becomes especially important as cuttlefish grow. Juveniles often rely more on camouflage, avoiding exposure. Adults, larger and more confident, use displays aggressively, hunting in broader areas and taking advantage of their visual dominance. The same skin that once hid them now becomes a lure. Humans observing cuttlefish often describe the experience as watching a living screen, patterns flickering and shifting with uncanny control. But beneath the spectacle is a practical function rooted in survival. The cuttlefish is not performing. It is manipulating perception. There is an important contrast here with many other marine animals featured in chemical warfare narratives. Poison punishes contact. Venom immobilizes through physiology. Ink erases presence. The cuttlefish operates upstream of all of that, targeting the decision point itself. By confusing prey before escape begins, it avoids the need for chemical escalation altogether. This has consequences for how we understand danger in marine environments. Not all threats announce themselves with pain or paralysis. Some operate quietly, turning sensory systems against themselves. The cuttlefish demonstrates that control over information can be as lethal as any toxin. The lack of poison does not make the cuttlefish harmless. For prey, it is devastating. The speed and precision of the tentacle strike leave no margin for error. For predators, the flashing displays can act as warnings or deterrents, signaling awareness and readiness. While cuttlefish are preyed upon by larger animals, their displays may reduce attack frequency by discouraging casual strikes. This dual use of visual signals, both offensive and defensive, makes the cuttlefish a master of open-sight warfare. It thrives where others hide, turning exposure into advantage. In environments where chemical weapons dominate, the cuttlefish proves that deception and timing can achieve similar outcomes without relying on toxins. As the cuttlefish feeds, its skin gradually settles into muted tones, the display fading as quickly as it appeared. The reef resumes its steady motion. Fish return to normal spacing. The moment passes as if nothing happened. But one less fish moves through the water now, and the balance shifts imperceptibly. This is why the cuttlefish matters in a story of unreal weapons. It reminds us that not all evolutionary cheats are chemical. Some are neurological. Some are optical. Some rely on understanding how other animals see the world and exploiting that understanding with ruthless efficiency. The ocean is full of poisons, venoms, and toxins, but it is also full of illusions. And sometimes, the most dangerous animals are the ones that never need to touch you until the very last instant. The reef never wastes anything. Every scrap of flesh, every fragment of shell, every drifting piece of decay becomes an opportunity for something waiting below. Along the boundary where sand meets rock, crabs emerge from cracks and shadows, legs ticking softly against stone as they move with deliberate purpose. They are not hunters in the dramatic sense. They do not chase down prey across open water or ambush from concealment with explosive speed. Instead, they arrive after danger has already passed, drawn by scent trails that tell a story of injury, death, or chemical chaos unfolding nearby. A crab pauses near a patch of reef, where venomous animals are common. Lionfish patrol these edges. Anemones sway just above the substrate. Sea slugs crawl openly, advertising their toxicity with bright color. This is not a safe neighborhood, but safety is not the crab's priority. Opportunity is. Crabs are built for mess. Their bodies are armored, jointed, compact, designed to wedge into tight spaces and survive impacts that would cripple softer animals. Their claws are not elegant weapons. They are tools for crushing, tearing, prying, and holding. In confined spaces, leverage matters more than speed, and few animals understand leverage like a crab. A single claw can apply immense pressure, cracking shells, snapping spines, and pinning struggling food against rock until resistance stops. But the most unsettling aspect of crab survival is not mechanical. It is chemical. Crabs are intimately tied to the movement of toxins through the reef. They feed where others hesitate, scavenging remains left behind by venomous encounters or chemical defenses. A fish killed by poison does not disappear. Its body sinks, carrying whatever toxins remain within its tissues. A crab finds it, tears into it, and consumes flesh that would sicken or kill more selective feeders. Many crabs tolerate these toxins far better than expected. Their physiology allows them to survive doses that disrupt other animals, either by metabolizing compounds more efficiently, sequestering them in less sensitive tissues, or simply enduring effects long enough to feed and retreat. This does not make them immune. It makes them resilient enough. That resilience has consequences. When a crab consumes toxic material, the chemistry does not always stop with digestion. Some compounds persist, accumulating within the crab's tissues over time. The crab does not become venomous in the active sense. It does not inject poison or sting. Instead, it becomes a bad meal, a carrier of chemical risk. Predators that eat it may experience illness, disorientation, or worse, depending on the toxin involved and the amount consumed. This is how poison spreads through the food web without intention. An anemone stings a fish. A crab eats the fish. Another predator eats the crab. At each step, the chemistry moves upward, diluted or concentrated depending on biology and behavior. The original weapon no longer belongs to the original animal. It has become ecological residue. Crabs exploit this dynamic unconsciously. They do not seek poison for defense, but their willingness to eat dangerous things gives them indirect protection. Predators learn that crabs are unpredictable meals. Some are harmless, some are not. In a reef where energy budgets are tight, unpredictability is often enough to discourage experimentation. This effect is amplified by where crabs choose to eat. Rather than feeding in open water, crabs drag food into crevices, under ledges, or into burrows where space is tight and escape routes are limited. Here, claws dominate. A predator attempting to steal food from a crab in a narrow crack risks injury to eyes, mouth, or fins. Combined with the possibility that the meal itself carries toxins, the cost of interference becomes high. Fights over scraps are common. Multiple crabs converge on the same prize, grappling in confined spaces where size matters less than grip and positioning. Limbs are lost. Shells crack. The contest ends not when one animal is killed, but when one can no longer hold on. These brutal encounters shape crab behavior, favoring aggression, persistence, and the ability to exploit chaos. From the reef's perspective, crabs are chemical recyclers. They do not neutralize toxins. They redistribute them. This affects everything from predator behavior to nutrient flow. Areas with high densities of venomous animals often attract more scavengers, including crabs, increasing the likelihood that toxins enter the scavenger network rather than dissipating harmlessly. This network is invisible but influential. Fish avoid feeding on certain crab populations. Predators adjust diets seasonally or regionally based on chemical risk. The reef becomes a patchwork of safe and unsafe meals, determined not just by species, but by what those species have been eating. Humans enter this system as accidental participants. In some regions, crabs harvested for food have been linked to toxin accumulation, depending on habitat and diet. The crab itself appears normal. It behaves normally. It is not poisonous by design, yet under certain conditions, consuming it can lead to serious illness. The danger is not universal, nor is it constant, but it underscores the same principle governing reef life. Chemistry travels. This is why traditional knowledge matters so much in coastal communities. Local experience often dictates when and where certain crabs are safe to eat, based on season, location, and observed conditions. The reef teaches these lessons slowly, and those who ignore them pay the price. Poison does not announce itself. It hides inside ordinary animals doing ordinary things. Back underwater, the crab finishes feeding and retreats, carrying fragments of food deeper into its shelter. Its legs move with steady purpose, antennae sampling the water, alert for approaching rivals. It is not aware of the chemistry it carries, only that it has survived another encounter in a dangerous place. Predators that patrol nearby hesitate when they see it. The crab is small, but not weak. Its claws are positioned forward, ready to strike in close quarters. The crevice behind it offers cover, and somewhere in the predator's memory is the knowledge that some crabs taste wrong, feel wrong, end badly. This is the quiet power of crabs in a chemically armed reef. They are not originators of poison. They are distributors. They turn isolated weapons into systemic risk, ensuring that chemical warfare does not remain localized. Every venomous sting, every toxic bite, every defensive secretion has the potential to echo outward through scavengers that refuse to let anything go to waste. Evolution rewards this refusal. By feeding where others cannot, crabs secure a constant supply of resources. By tolerating chemical danger, they gain indirect protection. By fighting brutally in confined spaces, they defend both food and territory with minimal movement. The result is an animal that thrives not despite danger, but because of it. As the reef settles and scavengers retreat back into shadow, the chemistry remains. It lingers in tissues, in memory, in altered behavior patterns that ripple outward. The original poison may be gone, diluted beyond detection, but its influence persists through animals that never evolved to make toxins themselves. This is why crabs matter in the story of unreal weapons. They remind us that chemical warfare in the ocean is not contained. It spreads, mutates, and reappears in unexpected places. The most dangerous meal is not always the one that looks threatening. Sometimes it is the one that already ate the threat for you. In a reef built on recycling and survival, nothing stays isolated for long. And crabs, moving patiently through the aftermath of every encounter, make sure of that. The reef narrows where rock meets shadow, forming corridors that feel more like architecture than habitat. Antennae extend from the darkness first, long and sensitive, sweeping the water in slow arcs, as if reading invisible currents. A lobster remains hidden inside a crevice, body pressed low, armor blending with stone. It does not rush out. It does not need to. In this world, survival is less about dominance in open space and more about choosing when not to be exposed. Lobsters live at the intersection of brute force and vulnerability. Their bodies are encased in hard exoskeletons, reinforced with calcium carbonate, layered plates designed to resist crushing, tearing, and abrasion. This armor protects against claws, teeth, and scraping jaws, but it is not absolute. Between the plates are joints. Beneath the shell are nerves, gills, and soft tissues that cannot be armored without sacrificing movement. Chemistry exploits these weaknesses with ease. The antennae continue to sweep. Lobsters rely heavily on chemical sensing, more than vision, more than hearing. The water is full of information, traces of food, rivals, predators, and danger dissolved into the current. A faint chemical signature drifts past the crevice. The lobster stiffens. This is not food. It is the lingering trace of an octopus. Octopuses are not armored. They do not confront lobsters head-on in open spaces unless conditions favor them. Instead, they approach through silence and scent, probing shelters with exploratory arms, testing reactions. A lobster knows this pattern well. The shell that protects it from a crushing bite offers no defense against venom delivered through a precise beak, or against arms that can immobilize joints one by one. Against chemistry and control, armor is only partial insurance. The lobster shifts deeper into its shelter, abdomen tucked, claws angled forward. This posture is defensive, but calculated. In tight spaces, the lobster's claws become devastating. Each claw is capable of delivering immense force, enough to crush shells, snap bones, or pin an attacker against rock. In confined quarters, leverage favors the lobster. It does not need to chase or pursue. It needs only to hold ground. This is the balance lobsters maintain throughout their lives. They are powerful, but not invincible. They dominate where space is limited and visibility is low, but they avoid open confrontations where speed, venom, or coordination could overwhelm them. Their survival strategy revolves around shelter selection, timing, and chemical awareness, rather than aggression alone. Chemical danger permeates the lobster's world. Moray eels lurk nearby, mouths lined with bacteria and capable of delivering deep, disabling bites. Sea snakes pass through cracks, venom potent enough to stop muscle movement entirely. Even small animals can pose chemical risks, from anemones lining crevices to toxic prey that could sicken a careless eater. The lobster cannot armor itself against all of this. Instead, it navigates around it. This navigation is not random. Lobsters choose shelters carefully, favoring crevices that limit entry angles and allow full use of their claws. They remember these shelters, returning to them repeatedly and defending them against rivals. Chemical cues play a critical role here. A shelter that smells of danger is avoided. One that smells of safety and familiarity becomes home. When confrontation does occur, it is swift and decisive. A Moray eel probes the edge of the crevice, jaws opening and closing in anticipation. The lobster responds instantly, claws snapping forward in a warning display. This is not bluff. In this narrow space, the lobster has the advantage. The eel hesitates. A damaged jaw or eye could mean starvation. The risk is not worth the reward. This is how physical weapons still matter in a chemical battlefield. Not all threats rely on toxins. Some rely on leverage, pressure, and the ability to inflict immediate mechanical damage. Lobsters excel at this, but only within the right context. Remove the shelter. Remove the crevice. The balance shifts. Octopuses exploit this shift expertly. They wait until lobsters venture out to forage, then strike in open terrain, where armor offers less protection. Arms wrap around the body, targeting joints and gills, applying pressure where shell plates cannot shield. A precise bite delivers venom that weakens muscles and disrupts coordination. The lobster's strength becomes irrelevant once movement is compromised. This selective vulnerability shapes lobster behavior profoundly. They forage cautiously, often at night, minimizing exposure. They move deliberately, antennae constantly sampling the water for chemical warning signs. They retreat quickly when unfamiliar scents appear. These behaviors reduce predation risk, but come at a cost. Time spent hiding is time not spent feeding or reproducing. Despite these constraints, lobsters thrive because they are adaptable. Their exoskeletons grow stronger with each molt. Their claws regenerate if lost. Their nervous systems learn from experience, associating certain chemical signatures with danger or safety. Over time, this learning creates individuals that navigate chemical minefields with increasing efficiency. Humans encounter lobsters differently, often misunderstanding where the danger truly lies. To people, lobsters appear slow, clumsy, even harmless outside of their claws. Handling injuries are common because this assumption is wrong. A lobster's claws close with remarkable speed and force, capable of breaking skin or crushing fingers. The injury is mechanical, not chemical, but it is no less real. The irony is that humans fear the wrong thing. There is no venom in a lobster's bite or claw. There is no poison to worry about in casual contact. The danger comes from underestimating leverage and reflex. Lobsters evolved to fight in tight spaces, and a human hand placed too close becomes just another object to pin and crush. This misunderstanding mirrors a broader theme in the reef. Not all danger announces itself chemically. Some danger comes from physics, from force applied efficiently in constrained environments. Lobsters are masters of this domain, turning narrow spaces into arenas where their design excels. From an ecological perspective, lobsters play a stabilizing role. They prey on smaller invertebrates, control populations of snails and other shelled animals, and compete with fish for shelter. Their presence influences where other animals choose to hide and feed. In areas where lobsters are abundant, certain prey species decline, while others flourish in the spaces lobsters cannot access. Chemical warfare still shapes these interactions indirectly. The presence of venomous predators limits lobster movement. Toxic prey influences diet choices. Chemical cues dictate shelter selection. Armor alone does not guarantee survival. It must be paired with awareness and strategy. As night deepens, the lobster emerges cautiously from its crevice. Antennae sweep wide, reading the water. No immediate danger registers. It moves forward, claws held low but ready, legs gripping rock with practiced ease. Every step is a negotiation with the chemical landscape around it. This is the reality lobsters inhabit. They are strong, but strength is conditional. They are armored, but armor is incomplete. In a reef saturated with chemical weapons, survival depends on knowing when armor is enough and when it is not. That is why lobsters matter in this story. They remind us that even the most physically formidable animals cannot ignore chemistry. Venom and toxins do not need to penetrate armor to be effective. They only need access to weakness, to joints, to behavior, to timing. The reef does not reward single solutions. It rewards combinations. Lobsters succeed not because their shells are impenetrable, but because they understand the limits of those shells. They choose shelters wisely. They fight only when conditions favor them. They retreat when chemistry tips the balance. As the lobster disappears back into shadow, the crevice returns to stillness. The armor remains, silent and waiting, part of a larger system where physical force and chemical threat constantly test each other. In this world, no defense is complete on its own, and survival belongs to those that respect every kind of weapon in play. The reef wall fractures into shadow where coral gives way to rock, and the water narrows into a geometry that favors patience over speed. Crevices open like mouths in the stone, some no wider than a forearm, others deep enough to swallow light itself. This is not empty space. It is occupied territory. A Moray eel lives here, its body threaded through the rock like a living cable, head protruding just enough to watch. Only the face is visible at first. Jaws open and close in a slow, rhythmic motion that looks like aggression to the untrained eye, but is nothing more than breathing. Morays ventilate their gills by pumping water through the mouth, a necessity in tight spaces where flow is limited. The motion is constant, mechanical and unsettling, teeth flashing again and again as if rehearsing violence. In reality, the eel is waiting. Waiting works here because geometry does the hunting. A fish passes too close, drawn by algae or small invertebrates clinging to the rock. The corridor is narrow, bordered by stone on both sides. Escape options are limited to forward or backward, and both routes funnel directly past the same opening. The Moray does not lunge wildly. It strikes with precision, head snapping forward in a sudden burst, jaws clamping down on flesh. There is no chase. The eel pulls backward instantly, retreating into the hole, dragging the prey with it. This is where the danger escalates. Inside the crevice, space collapses. The prey is pinned against rock, its body pressed into angles it cannot navigate. The eel's jaws tighten, teeth curving backward like hooks designed to prevent withdrawal. Morays possess a second set of jaws, pharyngeal jaws, hidden in the throat and capable of moving forward to grip prey and pull it deeper into the body. This adaptation allows the eel to feed in confined spaces where suction feeding would fail. Once seized, prey does not slip free. There is no venom involved in this process, no chemical injection, no toxin delivered through the bite. And yet the danger is real and severe because the bite is only the beginning. Moray teeth are sharp and numerous, built to puncture and hold rather than slice cleanly. When they penetrate flesh, they leave deep wounds that close poorly. In the wild, this means prey bleeds internally and externally as it is consumed. For animals that escape initial capture, the injury itself can be fatal later, impairing swimming or leading to infection. In the reef environment, infection is not an abstract risk. It is constant pressure. Moray mouths are not sterile spaces. They are environments rich in bacteria, adapted to warm, saline conditions. A bite introduces these microorganisms deep into tissue, bypassing surface defenses. For fish, this often means rapid deterioration if they survive the encounter. For humans, the risk is similar in principle, though context differs. This is why Morays are dangerous without venom. The harm is mechanical first, biological second. The geometry of the hole ensures that bites are deep. The structure of the teeth ensures that wounds are ragged. The microbial environment ensures that complications follow. In the reef, animals learn this lesson quickly. Fish avoid probing holes without visual confirmation. Cleaner species approach morays cautiously, performing mutualistic services that reduce parasite loads, but require precise signaling to avoid being mistaken for prey. Even predators larger than morays treat occupied crevices with respect. The hole itself becomes a warning sign. Morays exploit this reputation fully. They do not roam widely in search of food. They select good holes and let the reef move around them. Fish traffic concentrates along predictable routes, and the eel memorizes these patterns over time. Each successful strike reinforces the value of patience over pursuit. This strategy is energetically efficient. Morays have elongated bodies and reduced fins, making sustained open water swimming inefficient. Instead, they invest in jaw strength, sensory acuity, and spatial control. Their sense of smell is highly developed, allowing them to detect injured or stressed prey from a distance. Once prey enters the kill zone, the eel needs only a fraction of a second to act. The danger increases when multiple factors align. In narrow corridors, prey cannot turn effectively. Panic amplifies mistakes. Rock scrapes remove protective mucus from skin, increasing vulnerability. By the time the eel bites, the outcome is often decided. Humans intersect with this system most often through curiosity or carelessness. Hands reach into holes to steady a diver, retrieve a lost object, or explore what cannot be seen. This is a mistake rooted in misunderstanding. A hole in the reef is not empty space. It is private territory. When a moray bites a human, it is almost always defensive. The eel reacts to intrusion not as a predator, but as a territorial animal defending its shelter. The bite is fast and forceful, and the eel releases quickly once the threat withdraws. The injury, however, can be severe. Deep puncture wounds bleed heavily and can become infected if not treated properly. The pain is immediate, but the real danger develops over time. This delayed risk mirrors what happens to fish in the wild. Infection, tissue damage, and impaired function can turn a non-fatal encounter into a lethal one days later. In this sense, moray danger operates on a longer timeline than venom. It does not incapacitate instantly. It undermines survival gradually. The reef reinforces this lesson repeatedly. Fish with old bite scars swim poorly. Some develop fungal or bacterial growths around wounds. Others disappear entirely, removed not by the initial predator, but by the consequences of injury. Morays contribute to this invisible mortality, shaping populations not only through direct consumption, but through the wounds they leave behind. This makes morays important ecological regulators. They target prey that venture too close to shelter edges, often catching individuals that are inattentive, injured, or inexperienced. By removing these animals, morays indirectly select for better spatial awareness and risk assessment in prey populations. Over time, this influences behavior across entire communities. The whole advantage extends beyond hunting. Morays use their shelters as defensive fortresses. When threatened by larger predators, they retreat deeper, coiling their bodies into spaces too tight for pursuit. The same geometry that traps prey protects the eel. This dual function makes crevice selection critical. A good hole is both weapon and shield. Morays often maintain multiple shelters within a territory, moving between them depending on conditions. Some are positioned to intercept specific prey routes. Others offer refuge from dominant predators. Chemical cues play a role here as well. Morays can detect when a shelter has been disturbed or occupied, adjusting behavior accordingly. The interaction between morays and other reef predators highlights the complexity of non-venomous danger. Sharks, groupers, and large fish may attempt to prey on morays, but the risk of injury in confined spaces often deters them. A bite to the face or gills can be catastrophic. Even animals that can overpower a moray in open water hesitate when the fight must occur inside rock. This hesitation mirrors the broader theme of the reef's chemical battlefield. Not all threats rely on toxins. Some rely on architecture, bacteria, and the physics of space. Morays sit at the intersection of these forces, using environment and biology to amplify the consequences of contact. As the eel finishes feeding, fragments of prey drift outward from the crevice, carried by the current. Scavengers arrive soon after, crabs and small fish picking at remains. The chemical story continues. Blood in the water attracts attention. Bacteria bloom around organic debris. The reef absorbs the event, recycling it into nutrients and lessons. The moray settles back into stillness, jaws opening and closing as before. The teeth remain visible, a reminder of what occupies the whole. Fish adjust their routes. Hands should stay clear. The danger is not exaggerated. It is structural. This is why morays matter in a story about poison and unreal weapons. They demonstrate that not all lethal outcomes require venom. Sometimes the most dangerous part of an encounter is what follows: the infection, the impaired movement, the inability to recover in a world that does not forgive weakness. In the reef, survival is rarely about a single moment. It is about trajectories. A bite that does not kill today may kill tomorrow. A wound that slows movement invites another predator. A mistake at a hole echoes outward in time. The moray eel understands this, not consciously, but through evolution. It does not need poison to dominate its space. It needs teeth, patience, and a hole that turns escape into illusion. The sand looks empty until it moves. A faint outline appears first, a subtle distortion where texture shifts just enough to suggest something solid beneath. Grains slide, settle, and stop. What seemed like open ground is occupied. A stingray lies buried just below the surface, body flattened into the seabed so completely that water flows over it without disturbance. Eyes protrude slightly, scanning upward, while spiracles behind them pulse rhythmically, drawing water in for breathing. Everything else is still. This is not ambush in the traditional sense. The stingray is not hunting. It is waiting to be ignored. Shallow water is crowded water. Fish pass low over the sand. Predators cruise above. Humans wade, step, shuffle, assuming visibility equals safety. In this environment, danger does not chase you. It waits where you place your foot. A shadow crosses overhead. The stingray tenses almost imperceptibly, muscles along the tail tightening. It does not flee. Flight would require exposure, lifting its body from cover and announcing itself to whatever caused the disturbance. Instead, it prepares its only real weapon, a structure so effective it rarely needs to be used twice against the same threat. The tail whips upward in a sudden, explosive arc. The motion is faster than conscious thought. The barb rises from the sand like a blade drawn from hiding, serrated edges flashing briefly before contact. The strike is defensive, not targeted at vital organs, but designed to make contact anywhere it can. The goal is not to kill. The goal is to punish the mistake of touching what should not have been touched. Stingray barbs are modified dermal spines, rigid and sharp, with backward-facing serrations that resist removal once embedded. Along grooves in the spine lies venomous tissue, which ruptures upon penetration, releasing venom directly into the wound. The mechanics are brutally simple. Pressure triggers motion. Motion delivers puncture. Puncture delivers chemistry. For fish that attempt to bite or pin a stingray, the lesson is immediate. A predator that grabs the ray from above risks taking the barb into soft tissue, eyes, mouth, or gills. Even large predators recoil after contact, abandoning the ray and learning to avoid its shape altogether. The ray does not need to chase or fight. One strike reshapes behavior. The venom itself is not designed to paralyze instantly. It causes intense pain, tissue damage, and physiological stress that discourages further aggression. For a predator, the cost of attack outweighs the benefit of the meal. For the stingray, survival is secured without prolonged conflict. This strategy reflects the stingray's place in the ecosystem. Rays are not fast sprinters. Their bodies are built for gliding, not acceleration. They feed on benthic invertebrates, crushing shells with specialized plates rather than chasing fish. When threatened, escape is often impractical. Defense must be immediate and decisive. The sand provides concealment, but it also creates risk. Anything moving through shallow water can stumble into a stingray's personal space. The ray does not differentiate between predator and accident. Pressure is pressure. A looming shadow, a sudden footstep, a careless grab, all register the same way. The response is automatic. This is where stingrays intersect with humans most dangerously. People wading through shallow water often assume visibility equals safety. They step confidently, feet sinking slightly into sand, unaware of what lies beneath. A buried stingray feels the vibration and reacts. The barb strikes upward into the foot, ankle, or lower leg, embedding deeply. Pain is immediate and overwhelming, often described as intense, radiating, and difficult to ignore even momentarily. The injury is not just mechanical. The venom causes swelling, inflammation, and tissue damage that can complicate healing. In severe cases, depending on location and depth, injuries can affect tendons, nerves, or blood vessels. The backward serrations on the barb make removal difficult, and fragments can break off and remain embedded, increasing the risk of infection. This is not aggression. It is defense triggered by proximity. In the reef, fish learn quickly to avoid stepping on stingrays. Their bodies and fins glide above the sand rather than pressing into it. Predators approach rays cautiously, if at all. Humans, lacking this evolutionary context, often learn the lesson the hard way. The irony is that stingrays are generally calm animals. They do not seek confrontation. They do not pursue threats. They rely on camouflage and avoidance first. The barb is a last resort, deployed only when contact occurs or feels imminent. Most encounters end peacefully when the ray senses a distant presence and slips away beneath the sand. But mistakes happen. The danger is amplified by the environment. Shallow water concentrates interactions. Visibility can be distorted by glare, waves, or sediment. Feet, unlike fins, press down rather than glide. The stingray's defense is perfectly adapted to punish this specific kind of intrusion. From an ecological standpoint, the stingray's venomous barb is a stabilizing force. It allows rays to occupy productive feeding grounds without being constantly harassed by predators. This, in turn, influences benthic communities. Rays regulate populations of shell-forming invertebrates, aerate sediment through feeding, and create microhabitats that benefit smaller organisms. Their presence changes how animals move through shallow zones. Predators adjust hunting routes. Fish alter swimming height. Even large animals respect the risk of contact. The sand becomes a space that demands caution. The barb itself is periodically shed and regrown, ensuring it remains sharp and functional. This regeneration highlights how central the weapon is to the stingray's survival strategy. It is not an accessory. It is a core adaptation, as critical as wings are to birds or fins are to sharks. Unlike venomous fish that rely on spines embedded in fins or skin, the stingray's weapon is mobile. It can be aimed, raised, and deployed directionally. This gives the ray flexibility, allowing it to respond to threats from above or behind. The whip-like motion maximizes reach while minimizing exposure of the body. For fish that make contact and escape, the lesson persists. Pain and injury reinforce avoidance. Even without death, the behavioral impact is lasting. This is how chemical weapons shape ecosystems without constant use. The memory of pain does the work. Humans too carry that memory. Stories spread. Warnings are shared. Advice like shuffling feet rather than stepping becomes common knowledge in stingray habitats. This behavior reduces accidental encounters by alerting rays to approaching movement, giving them time to flee before contact occurs. The stingray benefits from this adaptation as well. Fewer strikes mean fewer risks of injury or broken barbs. Avoidance on both sides creates a fragile truce between animal and environment. As the tide shifts, the buried stingray senses the change. It lifts slightly, gliding free of the sand, wings undulating with slow, graceful power. The tail trails behind, barb held low now, no longer needed. The ray moves on to feed, crushing clams and worms hidden beneath the substrate, leaving behind faint depressions that will soon vanish. The sand smooths over again. The danger disappears from sight. This is why stingrays are such a fitting conclusion to a story about unreal weapons. Their defense is not flashy. It does not hunt you. It waits for you to make a mistake. It exists at the boundary between awareness and carelessness, punishing inattention rather than seeking conflict. In a reef saturated with venoms, toxins, illusions, and chemical traps, the stingray reminds us that some of the most effective weapons are passive until activated. They do not chase. They do not threaten. They simply respond. The ocean does not forgive ignorance, but it often allows learning. Stingrays embody that lesson perfectly. Step lightly. Look twice. Respect what you cannot see. Because sometimes the most dangerous blade in the sea is the one already under your feet.